Dear friends, dear students, very warm welcome to the celebration of National Science Day. And maybe some of you were present in the talk that was delivered by Professor Duncan Bhattacharya on last Friday. And why is this National Science Day? In fact, he explained it in great detail. Some people think it's the birthday of C V Raman. Some people think it's the discovery of the Raman effect. To be very precise, it was the press conference Raman organized to announce the discovery of Raman. He was, of course, a very proud and a very confident man. So he made a press conference to declare the discovery of this effect. And I think we should all learn from his spirit that you need to be confident and proud of your achievement. That's the spirit we should all learn from him. And this year's theme, how many of you know about the theme of this year? The theme of this year is the integrated approach of science and technology in sustainable future. So this is a very, very interesting theme, keeping in mind the nature of the interdisciplinary research that has become very, very important. That's an integrated approach. So science is not compartmentalized. Rather, it's an integrated approach. We cannot think of different compartments of science if we really have to make progress for the future. So that's the inherent message of this theme. And I'm very happy that a very nice program has been drawn to mark this occasion, which starts with 6 talks by 6 young people who are our future. And I'm sure that's going to reflect the research activity that is being carried out in our center. That will be followed by a debate. And the topic of the debate is slightly provocative, but I think it's very essential because we need to judge, are we really going uphill or downhill in terms of our science? The nature of doing science has also changed. Old times, science was much more individualistic. Now science has become a team game, much more interdisciplinary in nature. So the way we do science, that has also changed. So keeping in mind, I'm actually looking forward to this debate and what are the ideas that evolve out of this debate. And the very last session of this today's program, there will be a lecture delivered by Professor Gautam Menon, and who is basically going to capture the importance of interdisciplinary nature. And I think that goes very well with the theme of this year's National Day celebration. So with these few words, I welcome once again all of you to this program, and I'm looking forward to this program, which I'm sure is going to be very, very exciting. Thank you.
Thank you, Madam, for your inspiring words. I would like to invite our Dean Sir, Dean Academic Program, Professor Raman, for his speech.
Good afternoon. Welcome to the Science Day event at the National Center for Basic Sciences. This is a day of celebrating science in India and also celebrating science done by Indians. But I want to point out that for us at this center, every day is a science day. We do our science every day. We spend every day doing and thinking about science and trying to teach our students how to do it. Professor C V Raman was a nationalist. This is our director mentioned. The Science Day marks the date when we announced his discovery by a press conference. He was a nationalist. He dedicated his discovery to the nation. He cried at the Nobel Prize podium because there was no Indian flag when he received the medal. Now, today, as drums of war are beating once more across Europe and threatening to draw in every other nation, we should remember that science transcends national boundaries. But scientists cannot. We are social and political beings. We are conditioned and forced to remain anchored to places, to communities, and even to our ideas. Not necessarily the ones we are born with, not necessarily the ones we are born into, but any acclaim that our work receives is also an appreciation of where we are, where we come from, where we belong. So whenever our students see you do something good, some good science, we take pride in it. That we take pride in the fact that you trained with us and that you are a result of our training. Maybe not completely, you are also a result of who you are, where you come from. But we contributed a part to what you have become or what you will become. All science that you do also reflects on us, your teachers and your friends. And with that thought, I'd like to end my talk today and let the event begin. Thank you.
Thank you, sir. Now I would like to invite Professor Ajit Pitro to take the stage as the moderator of this session.
So, good afternoon, everybody. Science Day. So, what I request to all that science is not just solving some equations and doing some techniques. It is the scientific attitude that you should bring among people. That believing that everything has a reason and nothing is unreasonable. Science has every answer, and I teach my students in that way that try to answer all the happenings, and you will see that nothing is unanswerable. So science teaches that thing. So today, what we have, as Professor Sanders has already told you, that there are two events that will be performed by our students and colleagues. So the first part is some small talks by our PhD students. So we have chosen 6 students across 4 departments, and we have chosen the students in such a way that they should be presenting the state-of-the-art activity that particular department is going through. So as I understand that the science fraternity of this institute or center will now in a position that for a more collaborative or understanding what is happening in each department and in each individual. So they should have an essence of what good things we are doing individually or collectively. So there are 6 talks, 2 from CBMS and CMPMS each, one on theory, another experiment, and 1 talk will be from the astrophysics and cosmology department, and 1 talk from the theoretical science department. So we first request Ruchi Pandey from astrophysics and cosmology department to present an overview of what she is doing or what her department is doing. Ruchi.
I'm Ruchi Pandey and I'm a senior research fellow working in Department of Astrophysics and Cosmology under the supervision of Dr. Raman. And today I'll be talking.
I think
It's fine.
we can hear that.
And today I'll be talking about the astronomy and what type of research that our department is doing as a part of National Science Day 2022. So as you can see, the topic of my presentation is astronomy. What do we observe and how to make sense of it? So in this presentation, I'm going to give a brief overview of what is astronomy and what kind of work we are doing here. So I'm not going to go in very much technical details in this presentation. So now moving on, when we define astronomy, we say astronomy is the study of objects that lie beyond our planet Earth. That includes the stars that we can see in the night sky, all the planets in our solar systems, and even those objects which we cannot see from our naked eyes, that are very far away galaxies. For those which we require very advanced instruments and telescopes. Now, we also know that astronomy is one of the oldest science, and sometimes it is also known as observational science. What I mean by observational science is that we perform our test by observing something. And then we apply the laws of physics to understand the phenomena, what is happening there. And we also call it a historical science. By historical science, I want to say that what we have observed, it has already happened in the universe. We cannot do anything to change it. It's similar to the geologists. I mean, they cannot do anything. They cannot do anything to change the compositions of our planet. And just like the paleontologists, they cannot bring the dead animals back to life. In ancient astronomy, it was divided into basically two parts. One was observational astronomy, where people were collecting the data and by using telescopes and cameras, and other was theoretical astronomers. They were using the laws of physics and theories to explain the phenomena. Now, in modern astronomy, we can further divide these parts into various branches. I mean, there are many more other branches, but I'm showing here the few examples. So astrophysics physicists they use the laws of physics to understand, they use the laws of physics and apply in the observational data to understand what is happening there. And then we have astrometry, where they do the precise movement of, they study the precise movement of planets, suns, and moons. Then we have astrogeology, where the astrogeologists study the geology of planetary bodies and asteroids and comets in our solar system. And then astrobiology is theoretical science that deal with the life beyond our Earth. And then we have astrochemistry, where people study the chemistry and the abundances and the ions of space. Now, we are saying that astronomical objects, but how do we study them? All the information from any observational astrophysical object receives to us in form of light. So light is a very crucial to astronomical discovery. And but our human eye is also technically it's a detector, but our human eye can only detect in the visible light, and there's much more to light than our eye can see. Now we know that we use lights, but how we are gathering that light, how we are collecting that light. We need systems for measuring lights in astronomy. We require three basic components. So first is the telescope, which is also known as the buckets for collecting visible lights or other radiation at other wavelengths. Then we have instruments. These instruments, they are attached to the telescope, and they sort the incoming radiation by wavelengths. Suppose if you want to observe, if you want to filter the blue color of light so that we can measure the temperature of a star. And sometimes we want to measure the entire spectrum to see the chemical compositions and what are the physical properties of that astronomical object. And then third, we have detectors. These detectors, they permanently record the observations that we have made. Now moving on, we have, I have mentioned that we need telescopes. But where do we put these telescopes? As you can see, this is our Earth and this is our Earth atmosphere. So this is the electromagnetic spectrum from here we have gamma rays to radio waves. Gamma rays have small wavelength, high frequency, and radio waves have longer wavelength. But our Earth atmosphere is not transparent to all electromagnetic radiation. As you can see here, only a visible light and a small part of infrared and a large part of radio can penetrate the Earth atmosphere and reach the sea level. But now, so if we want to make observations in gamma rays and X-rays and in other wavelengths, we need to go in space. But now, one might ask question: if this light is coming on Earth, then why we are not observing only in this light? Why we have to observe in other wavelengths? Because each wavelength has its own significance and own importance while observing the things. Here is one of the, one of the big example I can give is the sun. Sun is the closest star to our Earth, and each and every observation in different wavelengths reveal different things. Now, moving on to different wavelengths. So first, why do we need, here I'm going to discuss why do we need different wavelengths. So first, we have gamma rays. They are energetic rays, and they are coming from the most energetic objects in the universe, mostly supernovae, supermassive black holes, and quasars. And this is an artistic diagram of one of NASA's Fermi satellite, which is work in gamma rays. And so this satellite is almost making discovery every day. They are discovering new supermassive black holes and large type of black holes. And our department is engaged in the study spectral and temporal properties of different active galactic nuclei using these Fermi satellites. Next, we have X-rays. So X-rays are also by more energetic processes in object. When the jets are superheated materials stream away from a black hole or supernovae, we see X-ray. And sometimes our sun also emits X-ray in terms of solar flares. This is Chandra satellite. It's one of the best satellites for observing X-rays by NASA. And now we have one of the national-based space observation facilities by ISRO, that is Astroset. And researchers in our department are also engaged in studying the data from Astroset. They are studying the accretion flow properties of high variable black holes. Now moving on to ultraviolet, these radiation falls in the wavelength range between 100 to 4,000 angstroms. So we typically use these ultraviolet radiation to reveal hot and newly formed stars, young stars. And these UV observations, they can also provide essential information about the evolution of galaxies. Then optical wavelength we have. This is optical is the light is how humans see the universe. I mean how we are seeing the planets, comets, and the sun, all the observable universe. And this is one of the famous telescopes, an optical Hubble Space Telescope. We have national ground-based observation facilities in India. So researchers from our department are using 2-meter Himalayan Chandra telescope at Ladakh, operated by IIM Bangalore. And then we are also using 3.6-meter Devkar optical telescope by Aries, and then 1.3-meter D40 by Aries. So here people are engaged in various research activities by using optical data, like they're studying the cataclysmic variable star system, they are exploding binary star systems, and they're also studying the 3D morphokinetic studies of different planetary nebulae. And again, they are from a Wolf-Rayet star to brown dwarf, and people are also studying star-forming regions and M-dwarf stars. Now, moving on to infrared wavelength. We all know that our ISM has so much dust, and visual light is obscured by dust. There's so much in our, even in our galaxy, which we cannot see by using visual light. So, to penetrate deeper into the galactic center or dust, we need an infrared wavelength. So basically, these IR lights is given by warm objects or protostars. These are stars which are about to be born, and we can look inside the stellar energy by using the infrared wavelengths, and it even gives them a peek at places like center of our galaxy, which is the things hidden behind a thick cloud of gas and dust. This is a national ground-based NIR facilities at 1.2-meter Mount Abu telescope operated by PRL, and researchers in our department, they are studying the molecules and dust in different astrophysical systems, that is planetary nebulae and cataclysmic variables, such as nova systems. And then we have a radio wavelength. So when we want to see what is happening inside the gas or dust clouds, we use radio wavelengths. And these radio wavelengths, they are immune to dust. They have a longer wavelength. And these are our one national facility, JMRT in India. And then this is one of the international facility, ALMA. So people at our department, they are studying the roles of outflow in star formation, and they are also studying morphologies of different galaxies using international facilities like ALMA and all. Then many people are also studying the X-rays and radio counterparts of galactic black holes. So that was the importance of studying the universe in multi-wavelength. I mean, by combining the results from all wavelength studies, we can find out, we can explore many things, and we can find out which process is more important there. So here you can see that this is the example of one galaxy, Andromeda galaxy. When you look at galaxy in the visible light, you might see billions of stars, but you're going to miss so much more details. If you look at the multi-wavelength images of the galaxy, then this multi-wavelength observations, they reveal different details that are hidden in the visible light alone. So at the end, I want to say it takes a team of people working together of different expertise, like gathering data, people experts in gathering data, people experts in performing numerical simulation, analyzing data to study the universe. And one of the best example of this teamwork is the recent image of black holes, which was generated by the Event Horizon Telescope collaborations. So basically they have used most of the Earth's ground-based observatories, and they use it as a virtual Earth-sized telescope to get this image. Thank you for your attention.
Very nice to see. And we will take one questions, three questions, maybe. Someone? Very? From online also? Okay, so let's thank Ruchi. Next, we invite Mr. Obi Ghosh-Moli, who is from CVM's department, and we'll be talking on simulation of software.
Hello. Thank you for the audible. Okay, so good afternoon, everyone. My senior told about the telescope, so I would like to discuss about the microscope, but biology under computational microscope. Okay, so at 1665, first human cell was captured through the microscope by the Robert Hooke. So we can say that that was the first baby step toward the biological research. But as time passed, that Francis Crick told that the ultimate aim of the modern movement in biology is in fact to explain all biology in terms of physics and chemistry. So I must say this field is such a field where physicists, chemists, biologists, mathematicians, computer scientists all working together. So that is a highly interdisciplinary field. So next, till now, what I get from the experimental biologists, to be precise, structural biologists, what they do, they gave us some atomic resolution of model of many molecules that are essential for life, like proteins, DNA. But that informations are tremendously helpful. But the main problem is they give the static picture. Suppose you went to see a football match and you are getting some snapshot of that match. So we will not understand properly what's going on. So we need the dynamic nature. As biological things like proteins or biomolecules, they are very much dynamic in nature. So they participate in various biological phenomena when they bind with something, with ligand or something like any kind of drug molecule binding. That happened due to the movement of the fluctuation of the biological protein, DNA, etc. So I will discuss about that thing mainly. So, but the problem is, from one thing I must tell that from experiment there are some methods which give the dynamical picture of the proteins. But the main problem is the resolution of spatial and temporal scale. So if we want to look at single molecule type thing, single molecule dynamics, single atomic motion. So for that case, experiment will not reach the fruitful result. And secondly, one thing I must say, the experimental result is based on some kind of ensemble average. So they are giving us an ensemble picture. But we need, if we need to understand the single molecular motion, we need to go to beyond that. So we believe on the computation and various mathematical technique, and we use that simulation, finally the simulation. So this is a typical timing and length scale of different simulation technique. So, and this is basically time scale, this is length scale. So I will mainly focus on this scale, that is all out of molecular dynamics simulation. Okay, so the question is, what is molecular dynamics? To understand the molecular dynamics, so molecular dynamics is a computer simulation method for analyzing the physical movement of atoms and molecules. But if you want to understand the molecular dynamics, we need to be on class 7 physical science. That's Newton law. They are governed by mainly Newton law. So how it is used? So this is from physics, and we use that mathematical tree, Taylor expansion. So I have some position, current position. I know my previous position, and if I know the force interacting between the particles, I can calculate what will be its next position. Okay, so this is mainly behind the molecular dynamics. So this is if I have the position T minus delta T and T, from that I calculate the force, and next from that I can calculate the time next position at T plus delta T. So this is basically molecular dynamics which we use in biological research. So how we will use, I will tell one by one. Okay, so in this I must say one thing, that first ever molecular simulation of liquid argon using the linear position done by the Raman. So he was an Indian and he did it on 1964. And secondly, we must say that he is the pioneer in the application of computer method to the physical system. So he is a pioneer. So and he is an Indian. Okay. And on 2013, Martin Karplus, Michael Levitt, and Arya Watson get the Nobel Prize for the development of multi-stage model or complex chemical system. So I just tell about the pioneers who are working in this field. I will tell about what they did actually, what is the how we apply the molecular dynamics one by one. Okay. I told about the biomolecular system. So just to give a small taste of the what is the protein. The protein is a basically building block of the body. Now how protein made? Protein made using the well-known amino acid. So we have that know that there are 20 amino acids that vary in side change composition, and they become sometimes there are some hydrophobic, hydrophilic, and this amino acid together form this type of chain, and this chain sometimes fold and make a proper protein. So this is proteins. Actually, this sequence of amino acid is protein's primary structure, and when they fold, they got a secondary structure. There are sometimes there is some misfolding happen that they are not properly fold, and as a result, there are very different types of disease may occur, like Alzheimer, all those. So this is a properly folded protein, that's the ubiquitin protein. This type is helical structure they have. This is crystal crystal structure. We get this thing from X-ray crystallography, and this actually protein looks like this. Okay. So I told about the protein structure, but I am interested in the dynamics of the protein. So if you want to know the dynamics of any system, we need to know what's the degrees of freedom. In case of protein, we use the degrees of freedom phi and psi. So what is phi and psi? This is a diagonal angle. We know the diagonal angle between the plane. We did it in class 11 class or 12 mathematics. So we use that same technique to find the diagonal angle of the protein. So diagonal angle is basically this C alpha 3 atom made by these 3 atoms, plane made by these 3 atoms, and N C alpha C. The movement between this plane is defined as diagonal angle phi, and N C alpha C N. These two planes make the diagonal angle psi. Now I must mention one thing. G.N. Ramachandran, a famous scientist, he on 1966 he proposed he did some experiment and told the possible combination of phi and psi. And from that possible combination, what type of structure actually protein made? Because I told that there are some kind of helix structure, sometimes there is sheet structure. So if you know the pulsar, you can predict what type of structure that protein has. So G. N. Ramachandran first did the experiment, he proposed this thing, and incidentally he is a student of C. V. Raman. So this was the currently biologists are using, not biologists, every experiment is using this Ramachandran plot rigorous. Okay. So I told on much that slide of Newton's law of motion. I told about the force. So we need the interaction force. So force is basically minus gradient over potential. Now, what is force field? Force field is computational method that is used to estimate forces between atoms, within molecule, and also between the molecules. So we need this because from force only we can calculate our next position. I have the current position, I know it. What will be my next position? That will be calculated using this force. I already told that on that slide. Now, how this force actually, force is basically from this potential. The potential is basically written as proteins bonded and non-bonded interaction. So bonded interaction means sometimes you can think of protein to atom as they are stretchy. Sometimes the angle between them. So these all things are basically calculated as energy as E bonded, and there are some non-bonded interaction like van der Waals electrostatic interaction between the atoms. They can be modeled as a separate term. So this is the total form, some empirical form of the force field, which we use during our simulation and use the trajectory. We get the trajectory of the any biomolecular dynamics or biomolecular protein. Okay. So till now I discussed about the molecular dynamics slightly and how we use what is the force field. Currently there are lots of force fields available, and they are actually very much well suited with the experimental result. So I will show one result where I did the simulation and I compared the result with the experiment. So I will show it. So till now, example of biomolecular process that have been examined using molecular dynamics. Like sometimes we have the cell membrane. So sometimes transport small molecules across the membrane. Sometimes ligand binding. I will tell about this thing mainly. So in ligand binding or sometimes conformation change. Biomolecules like protein, sometimes in our body they work when they got a specific conformation. So something bind. So this is this ligand or small molecule bind and then conformation change, and then they start to working in some species. They participate in some kind of special biophysical activity. So the same thing is work in case of drug. Okay, and protein folding. So these all are basically examined clearly using the molecular dynamics. So if you have a computation power, if you create that sequence, take the sequence of that amino acid and do the molecular dynamic simulation, at long time it will properly fold and give you the proper protein structure which is compatible with the experimental structure. Okay, so I will emphasize on just two slides on the ligand binding. So ligand binding, protein has small molecule ligand play a key role in intracellular signaling. Now, if the ligand are drug molecule, then it will be helpful for treatment of disease. And thirdly, sometimes ligand affect protein function or blocking the active site like this, or by causing the protein to adopt the functionally altered conformation state. So what I told actually is a ligand bind, its state change, and it will participate in various biophysical activity. Till now, I told about how MD can be used various biophysical activity. So next, what I did, I just want to tell, I try to tell in a lucid way what type of thing I do. I did it. So in case of protein ligand system application, so there protein has two states basically, unfolded and folded. In between there is a state that's a molten glucose state. Okay, so experimentally you cannot capture this thing properly because you cannot crystallize the molten glucose state. Now, if you use some kind of denaturant like urea, heat, or extreme pH, you can find the protein molten glucose state. Now, why this is important? Now, alpha-lactalbumin is a protein which is present in mammalian milk, which control the formation of lactose in the milk. Now, at low pH, the alpha-lactalbumin became converted to molten glucose state, and at molten glucose state, when it binds with the oleic acid, it will form the samlet-like thing which shows the cytotoxic activity against the cancer cell. So that is the motivation behind this work. And what I did, I actually, if you take a protein and if you take that oleic acid ligand, you just do the molecular simulation. If you have the computation power, ligand will automatically come and bind with the protein. But we have the limitation of computation power. We do not run it for millisecond or microsecond, millisecond time scale. So what we take the protein and keep the oleic acid in near a specific place near the protein. So how do we identify that specific place where ligand will bind? We'll got it from the experiment. So experimentally, sometimes we will told okay that in protein this place is active site, so ligand will bind here. So we use that information and we dock means in a lucid way. We have the protein, we know that okay this portion ligand will bind, so we just keep the ligand on that position, so that it is easy for us to get the stable structure soon. So we did the molecular dynamic simulation. So this is some kind of characterization. I will just go through in a lucid way. So it's RMSD plot, that is a fluctuation of the protein. So if you run in a field, if you run alone, and if you take some monkey on your head and you run, so you will be less stabilized. Okay, when you are with the monkey, you will run not so fast. Okay, so that similar thing happened in this protein. The black line is just basically a simple protein, but so it has a fluctuation high, and this one is also a fluctuation parameter RMSF, and so the black line is showing the protein is fluctuating. But when the ligand is coming with it, this fluctuation becomes less. So similar thing happened here, and what we find that in presence of ligand, protein is stabilized. So don't forget that my aim is to study that binding of that ligand with the protein, because it shows the cytotoxic activity against the cancer cell. Now what is the experimental quantity with which we can relate? That's the binding energy. Now people told calculate the binding energies that this amount of binding energy this specific protein has with the oleic acid. We can calculate the binding energy. So we know the binding energy is if we remove one particle, so what is the energy required for those? So we did the similar thing. That's something. This is we just pull the ligand from the protein, and at each step we did the simulation, and from using some statistical method we calculate the free energy. So you can find one thing: when the ligand is far distance, we will not feel the interaction, but when it coming down, this is the distance. So distance from the ligand and proteins. So far distance is the ligand is in distant place. Now I'm pulling this. We are pulling near the protein, and what we get at long time, log distance, energy is feeling zero. But as protein approach, energy is going downward. So the system are going to be stabilized. And the difference between this will give the binding energy theoretically. So what we get the binding energy is minus 10.36 kilocalorie, whereas from experiment we are getting this. So my motivation is showing this thing is we are doing some empty calculation. We are doing this from some model-like thing, but we are relating our result with the experience. So finally, I must say, I hope you will convince that everything that living things do can be understood in terms of the sibling and willing of atoms. So this is our basically bottom to top approach, basically. So thank you.
Very nice. Okay. Any question? Quick question? Someone? Oh, yeah.
Nice talk about so you calculated the EMF, yeah? So did you run multiple simulation or?
So in now I have done one simulation. I need to explain this on the under. So I need the multiple solution, then the error bars, all those things.
Okay.
So it is actually not published, just under.
Okay. Yeah, that's fine.
Okay, so thank you. Very nice talk. So next we have Oishoryo. Oishoryo is from CMKBS department, and he will be mostly talking about the simulation studies.
I think I can get PDFs. So good afternoon everyone. My name is Ashoka Ghosh, and today I'll basically be talking about computational material science. While what and how we do it, I will be talking in a very generic manner and not talking in details about. But I also will be talking about the things we do in department, but I'll try to make it so that everyone can understand. So the history of human civilization can be seen as a series of breakthroughs in terms of chemistry and material science, starting from Stone Age to Bronze Age. Bronze Age have come to this iron and silicon carbon age. These materials have always lent their name to the ages because it actually leads to technical advancement, which then lead to the advancements of our era. So then you can see that this actually will shape the history and also the political power, the military and the society all over. So we have this iron and steel which has helped us in building and concrete even, which has helped in building our industries and roads and all that. Uranium, plutonium are giving us power, and silicon-based electronics are in every round of us. So materials basically pave the pathway for advancement of man. So we also have material challenges. In terms of technology, it has always been benefited by the discovery of advanced materials. And even today, there are many technologies which are not actually at the aim of their opportunities, which can do much better than they are today. So there are material challenges. Take for example, this solar power. Solar cells has been discovered like 100 years from today, from where it is also not its optimal power. If we talk about electrical vehicles, which are the eco-friendly mode of transportation, it can do better in terms of batteries. We can have lightweight, high-strength materials to help our avionics, so that we can reduce the cost of fuel. We can have high temperature durability, so that we can run our thermodynamic cycles better to be used in our furnace and turbines, etc. So none of these technologies are close to meeting their potentials, and there are much work to be done. So why do we do it? What is the motivation for this studying fundamental physics? So basically, it cannot be said exactly for everyone, but there are some points I think most of you will learn. So one of the most important points is that the macroscopic properties that we study are actually lead to relevant modern technologies. So these properties actually define how a material is, how strong it is, how in quantum electricity, how it behaves magnetically, and so on. And so you have to remember that this is the field that we actually give us semiconductors and transistors. And nowadays it also overlaps with biology, biochemistry, biotechnology. So it's always at the aim of applied science and next-gen technologies. And then obviously there is a very obvious point is this basic physics motivation, because ultimately the microscopic properties that we are studying, it has behind it a very important and interesting basic physics. So and there is always room for new developments in these fields. And in many of the cases there will be quantum mechanical behaviors, and actually we will be applying these ideas that we learned in quantum mechanics to cases where the technical consequences are important. You also can take, for example, the case of superconductivity, where a new field of study and theories have been developed because the quantum matter physics test. And this third point, I do not know if it should come on the purview of motivation, but it's very important. It's interesting to know that it's a strong indicator that CMP has led and will continue to lead the understanding of very, very important physics and will changing the life of people for years to come. It's tantamount from the fact that in the last 20 years, more than 25 Nobel Prizes were awarded. But there are challenges. So when we are doing this physics, we have to consider a variety of effects, starting from very small length scale quantum interactions like charge of spin transport to macroscopic properties at very large length scales, such as structure information and craft population. We also have to handle the large degrees of freedom in terms of structure and composition. So if we take the elements from periodic table, we can have billions of combinations. All this makes the study very difficult with the computational techniques. It can actually be a groundwork and help experimentation in the sense that going the trial and error route is not very optimal. So we don't have the time or resource to explore all the options experimentation. So what encompasses discovery through simulation? We now have at our disposal a plethora of tools for characterization and simulation and modeling of materials and chemical systems. So this gives us an unprecedented view into the realm of the atomic scale, and we can actually model and characterize materials in the scale where such behaviors are controlled. So obviously we'll be needing better computational power, and in previous 20, 30, 40 years, we have seen a huge development in this field. Okay. So, I'll be mostly talking about how memory has developed over time and then also physical science. So in 1952, we had this IBM 726, which could carry only 2.3 megabits of data, but almost as tall as me, I guess. And then in 1980s, we have these hard disks, which are smaller in size and could carry actually 5 megabytes of data. But remember, 5 megabytes is much smaller than even one picture you take in your smartphone today. Then we also had the floppy disks. These are not 3D printed cell buttons and floppy disks. and then these are basically to carry 1 to 4 megabytes of data. Then jump to the 90s, we have the CD read write drives, and they could carry 700 megabytes of data. And at today's age, we can carry almost 32 GB of data in a small cell like this. And in a different variant, it can go up to 1 terabytes. So this is a very nice representation of how hard-disk space has evolved over time. You can see it has always grown up exponentially. But not only about space, computation is all about all these factors like how much power is drawing, number of logical cores, and frequency. All these has grown up exponentially in the last 40 years. And not only about hardware, we can also talk about software, how we get a large data, fragment them, and then process them and so on. So I like to quickly plug in the computational facility of at our institute, and we have very nice facilities that you all know about, and like the HPC, the UNAS, and AMDU, where we can work on parallel and photon and all these we can work on serial, and they all have nice CPUs and RAMs. And I'm very glad to say that HPC has been listed within top 50 supercomputers in India based on survey that was carried out by CDAC Bangalore in 2021. So all this is really nice. So what we do and how we do it. So here I have like 3 classes of work that we do, but obviously this is not an extensive list. There are many more things we do, but this will get you started and get some idea. So, and how we do it, we have already seen this slide with the slide. So sort of the tools of theory that we use depends on the length scale and time scale. And so these are some of the ideas that we use. For so in small length scale, in quantum mechanical domain, we can use something like density function theory. Then as with the set, we can also use molecular dynamics in an intermediate stage. And beyond that, it is all under the purview of kinetic theories. So I will now come to this first principle-based exploration of ground state properties of materials. So one of the ways that this theory is done is we take an experimental observation and then we try to fit a model into it into empirical or semi-empirical model. And then we can also extrapolate it to other cases. I mean, not always, but there is a scope that we can do it. But the problem with that is that the system is very complex and modeling is very difficult. So it is the purview of it is quite limited. So what first principle calculation does, it takes a different route. It starts from very basic physical properties and ideas that you already know. That a system is made of atoms. An atom are made of positive core and electrons. And all the interaction between two systems, the interaction that the bonds are formed with these interactions. And so if you can very nicely model those interactions, you will be able to have this very intrinsic physical quantities and ideas come out of a calculation. So what makes first principle calculation difficult is not so much the complexity of the physics. Obviously, you have to model those interactions accurately, but they are somehow, but also rather the size of the problem in terms of numerical formulation. So you also have to formulate this so that we can handle those data and do the calculation nicely in a possible amount of time. So some examples that include is like theories that can be used. The common principle is legendry function theory, Ashoka, and so on. So using these tools can explore structure, dynamics, electronic and magnetic properties of very simple to complex systems. So there is some work that has been done in our department. In our first work, authors have employed first principle electronic structure calculation to investigate the stability electronic magnetic properties of this ordered double transition metal two-dimensional maxine compounds. So they have figured out 3 narrow gas semiconducting compounds, TIM2, C3F2, and all 3. And beyond that, they have also used thermoelectric properties, calculated thermoelectric properties, and finally projected that TIM2 and C3F2 is a very nice thermoelectric material with GT value higher than 1 with the last temperature range upon P-type carrier 2. In another work, the authors have examined the evolution of electronic structure in twisted bilayer of MOSA2. Its role in modifying the electronic structure is probed by mapping this gas structure into a primitive cell, which will represent untwisted limit. At large twist angles, we do not see any difference from the primitive cell, but at small twist angles, some regions of enhanced interlayer hopping interaction strength appears, and hence such perturbation leading to subband formation, which is also can be seen localized in both real space and quantum space. Next is obviously the modeling of noble materials. So the field of computational material science, it comes with the promise of designing materials with properties of choice. And in even literature, there are many instances you will see where such calculation has actually helped in simulation and manufacturing of interesting materials. This is actually the dream of material by design, and it was first used by the scientist named Michael Ashford, under whose name this SB plots come. This is an interesting plot that it will actually plot two properties and then plot materials which will come under one family. These white spaces are important. This is where maybe interesting properties can lie, but they have not yet been discovered. So what we try to do is to explore the unexplored part of the computational space. So this can start from some chemical intuitions, or it can be inspired by already present moduli of interesting materials. And nowadays we also have this approach of data informatics, and where we have large amount of high throughput data stored, like in Meta's Genome Project, there are other things like OPMD and so on, from which we can also get enough ideas. And after everything is done, we can also check our candidate material for different properties and stability and so on. So the tools that we will use, the software packages that we will use will depend on the problem at hand. So you can use first principle quantum mechanical calculations, or small length scale atmospheric simulation on a bit larger length scale. You can also use force and potential, some of which we already talked about. So this is another work we have done in which might come under the purview of material by design, where you have used a combination of computational tools, a machine learning technique for screening of stable candidates that can come under double press structure, and then the structures which are predicted to be double press with high possibility, they have used an evolutionary algorithm for crystal structure determination, and finally a fast visual calculation done on the structure for characterization of electromagnetic properties. And after this exercise, they've actually predicted 21 double press of varying magnetic and electronic properties. All those can be seen in this slide. So finally, we come to this data-driven machine learning approach. So with a large amount of data that's been generated nowadays, computational learning using algorithms to learn the patterns between data and then use those ideas to make predictions and becoming very widespread. So and actually, it is much faster than simulation, but can give you the accuracy of simulation almost in that order. So how it works is basically we start with the data set, which will be constructed of instances or the cases in the data set, attributes which can be some physical or chemical properties of each cases. And then we also have a final class upon which will be, predicting maybe classification problem or regression problem, that will depend. And with the data, we'll do some sort of pre-processing, like normalization and handling of imbalance. All these things are required so that it can actually build a meaningful model. We also can select the attributes that will be used in model building. And in the next part, in the model selection part, we have to actually use, maybe we can try different algorithms and see which is giving the most, the better performance than anything else. And this simulation is basically done on a held out set. So the model will be built on its data that is, and then the prediction will be done, the evaluation will be done on a set that is not seen by the model training part. There is no issue in that. And then there are matrices that we use for that. And then after you have built the model, you can do prediction on the unseen data and then go on about with it. So you have a very easy example to understand. Suppose you have data from few years about each day, about the temperature, humidity, and wind speed, upon which rain generally depends. And then we also have the data whether that day saw rain or not. And if we can use an algorithm to train on this data and then feed today's attribute values of temperature, humidity, and wind speed, then it will possibly figure out the probability of rain today, whether it happened or not, and with what probability. So here's one example that we have worked on. We basically employed a combination of machine learning and first principle calculation to suggest rare earth living magnets. So basically, the training set is built from experimental data, and it can actually skew out magnetic transition temperature, saturation magnetization, whether it is greater than 1 Tesla, or the nature of magnetization anisotropy, whether it is greater than 0. And we have actually, after we build this model, we have tried to use this radium-based candidates, and have put this into the model, and we have actually seen that in cases of age life between 0 to 7, all these things actually are valid. That the PC is greater than 600, we know MS is 1 Tesla, greater than 1 Tesla. So, and then finally, we have also used a DFT calculation to validate and see that the prediction of machine learning actually matches with the calculations. So, I'm at the end of it. So, the basic recap will be that with many advances in past decades, we have seen an era of computational materials research, and the role of the simulation can range from finding properties to new materials and 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 machine learning data-driven approaches also. And recently, and this is very important, that researchers have incorporated all over the world into material informatics. So now we have a huge amount of data in various repositories which can use actually guide in our work. This is also thank you for your time.
Summing up the different approaches of studies, material sciences. Anybody, any question?
I have just a comment to make. Computational talk. It's actually very nice that SNBNCBS Center has been chosen as one of the 9 institutes where the supercomputer will be built with a capacity of 1 teraflop, and that will be basically commissioned by CDAC Bangalore. So this will boost the computational power even.
Okay, so very nice. Next we have Shurjana Panda from CMPMS department, who will be talking on the experimental algebra of his department. You can remove this.
Good afternoon, everyone. Myself, Suryanarayan Panda, and in this talk, I am just going to give you an overview that what type of experiment we do, and what are the fields we cover, what are the instruments are there in our this condensed matter physics and material science experimental department. And these are the faculties: Professor Ranjan Verma, Professor Abhidranath Pal, Professor Bangali Bose, Professor Kalyan Manda, Professor T. Sethi, Professor Abhijit Chaudhary, and Professor Nitesh Kumar. Generally, in this, in our department, we make some very delicate samples by the fabrication technique, and we characterize those samples and try to underpin the interesting phenomena exist in those samples, and the research interest, that what are the research and what are the fields we cover and our achievements. So I will first explain that how we are going to fabricate the interesting samples. So we have a very good clean room facility, and there you can say to make thin film samples, we have 3 techniques. One is the electron beam evaporation, one is the RFDC Menon sputtering, one other is the pulse laser deposition. You can say there is a substrate on which we want to deposit our sample, and there is some materials. These materials we want to deposit on those substrate. So by using electron beam, if we deposit those samples, we'll excite through the electron beam, the atoms will come out of those target material, and these materials will be directed towards the substrate. This is the phenomena which, when it is used by when it is done by using electron beam, then it is electron beam evaporation. When it is been used, we use some inert gas in a plasma mode, then it is RFDC Menon sputtering, and when the pulse laser is being used, then it is pulse laser deposition. and this is the electron beam lithography and focused ion beam. It is used for the patterning. Means there are some thin film, and we want to etch out some of the portion, and there will be some spots, island type of spot. So this machine is used for that type of purpose. And this is when we deposit all our samples, there will be some edges, means unwanted materials. To etch out all those, we use this inductive coupled plasma reactive ion etching system, which is also called ICPR. Also, there is, by using some chemical method, we could deposit our samples, which is called the atomic layer deposition technique. And other than this, these are the thin films. And when we want to make some nanoparticles, there are some different techniques. We use furnace, we used RF induction melting spinning furnace, or rapid thermal annealing process furnace, and spin coating system. And electrochemical deposition is another method by which we use the electrochemical method. There is a solution, and the anion will be deposited on the cathode, positive electrode. And these are the few methods. Other than this, there is a chemical lab where we use different chemicals for making nanoparticles, and there are some other instruments also under different faculties. And after making those samples, we want to extract that what are the other physical phenomena, whether it is magnetic, whether it is non-magnetic, whether there is some superconductivity inside this. So we want to know, for which we have to characterize those. So what are the characterization methods? So these are starting from here. This is the to know it is magnetic or not. We use vibrating sample magnetometer. It can be temperature dependent. We want to measure the these magnetic moments with different field and different temperature. And this is X-ray diffraction. Whether we want to know that this sample is amorphous or crystalline. So we use this X-ray diffraction. Also to know if there is a thin film, what is the thickness of this film. Also whether it is amorphous, there will be no spectra from this XRD. So I am not showing the experimental results. You can go directly to the institute website and to know that how the spectra look like. The profilometer also give us the thickness and how the surface look like, what is the roughness of the sample, what is the nanoparticle size. If you want to know, then you can use FESEM, this scanning electron microscope. Also this atomic force microscopy is used also to know the topographical roughness and sample thickness also. Also in this build-up also there is two systems. One is the magnetic force microscopy, another is the atomic force microscopy. Atomic force microscopy only sense the van der force, and the magnetic force microscopy, the tip is made of some magnetic material, so it will sense the magnetic force. So this will give you some interesting phenomena like Scarmian vortex. Then these are the magnetic size of island. Island, it will say these are structures. So
good afternoon, everyone. I'm Neeraj Kumar, a senior research fellow working in theoretical science department of this institute, and I welcome you all on this National Science Day celebration. So today I'll be talking about theoretical aspects of the black hole, which my group is interested in, and we do much more things than just this. So, but this is what my expertise is. So I'll be talking about this. So the aim of the talk is to impart some excitement about the black holes which we share. I'll briefly give you an overview of general relativity, and then I'll come to the classical black hole solutions in general relativity. And then the main part of the talk, which is about the second law of thermodynamics and black holes, which we are interested in. And I also give you a very lightning review of quantum physics, which is used to understand the black hole radiations. And I'll conclude. So theoretically, black holes are solutions to Einstein's equation in general relativity. Black holes are solutions to Einstein's equation in general relativity. And what general relativity is? It can simply be summed in these Einstein's equations, which says that the space-time geometry is equal to the energy of the matter field, which can simply be put in very simple words by Professor John Wheeler, which say, and according to this equation can be summed up simply to space-time tells matter how to move and matter tells space-time how to curve. So geometry is basically, so gravity is basically geometry. And gravity is not like other three fundamental forces. So inertial particles follow shortest paths in curved space-time, which are called geodesics, which gives an impression that the particle is accelerated if the curvature is not there. It hinges on two very important principles. One is the principle of relativity, which gives us the notion of space-time, which says that the time is relative, and it gives us a new sense of causality itself. Very different from Newtonian mechanics. So time intervals measured by different observers are different for in relativity. And another very important principle is which simply says that the inertial mass, which comes from the second law of Newton's second law, and is equal to the gravitational mass, which is from the Newton's law of gravitation. So in Newton's gravity or Newton's theory, it's not a priori. It's not okay to assume that the masses should be same. So these two principles have been tested time and again to a great level of precision and recently microscope is a facility which is a space-based facility and which tested principle of equivalence with a precision of the order of 10 to the power minus 15 in 2017. Also, these principles are under constant scrutiny by new gravitational wave detection experiments. Let's come to Einstein's equation now. A solution of Einstein's equation doesn't simply mean finding the form of the space-time for a given energy of matter fields. Since matter depends on the dynamics of the fields, which is simply like motion of particles, and which in turn depends on space-time. Yeah. So Einstein's equations are highly nonlinear coupled differential equations, which should be solved simultaneously to find the geometry of the space-time and matter distributed in it. Only solutions with very high symmetry are possible to find exactly. And Minkowski space-time, which is a flat space-time solution, is one of the solutions, one of the trivial solutions of Einstein's equation. Here, this is the picture of this flat Minkowski space. Here, the dotted lines are light rays, and inside these dotted lines, it's a closed curve. Okay, so it's a cone, yeah, and particles with massive particles follow paths in these this light cone, and away from this event, which is in pink, is orange here. So orange, we don't have any connectivity towards to other points, which means that these points are causally disconnected to this point, and these are space-like points. Now come to the solution of black hole. First classical black hole solution was discovered in 1916 by Carl Schwarzschild, and it wasn't taken seriously till 60s as the solution had a singularity. By singularity, we mean that the curvature of the space-time diverges at that point. So, Schwarzschild black hole solution is in general a static, spherically symmetric mass distribution outside its radius, but becomes a black hole when the radius of the mass becomes smaller than a value called Schwarzschild radius. Yes. So this is the cartoon picture of Schwarzschild black hole, where the singularity is staying here, and this surface, this ring is called horizon. This is called event horizon, and the observers from here far away are Minkowskian in some sense, so it's asymptotically Minkowski. And anything which goes inside once and crosses the horizon will definitely fall into this singularity. And this is a much more causal and elaborative picture of this black hole solution. So this dotted line is representing the event horizon, which is very important for us. as it's mostly all the properties of the black hole are associated with event horizon. So very far away from the event horizon, the space-time is again this Minkowski flat, I would say, and the Gautam structure is same as that of Minkowski space. But as you go more closer to the horizon, this light cone is shrinking. So it says that to an observer, which is outside, staying here, can never and observes a particle which is crossing the horizon or something, will never see the particle crossing the horizon. But this is not the actual thing, because particle can definitely cross the horizon in his own time. He can see, the particle can definitely cross the horizon and reach this. This is the singular point. So inside, if you see this light cone takes this Gautam structure inside takes this form. So so these are the light paths at the boundary, and any messy particle will be moving towards the horizon. So you can see that any particle which is once inside can never turn back and come out outside the black hole, the horizon. Well, another very important question: how many different types of black holes are possible? And the answer is not many. Social black hole is fully characterized by its mass only. Most general black holes are totally defined by their masses, charge, and angular momentum. And this comes from a theorem in gravity, which is called no-hair theorem. Imagine this. This is the mass distribution, different type of mass distribution, which is collapsing and forming a black hole. So the general thought may be that it can collapse to this state, or this state, which is like keeping some memory of its original form. But this doesn't happen. No-hair theorem says that all kind of different distributions will definitely end up to a singularity, which is here and which is covered by this horizon. Now coming to the black holes and its connection to other parts of physics, especially thermodynamics. So the second law of thermodynamics simply says that the net entropy change in any physical process of a system and surrounding taken together should be either positive or zero. John Wheeler assigned a problem, PhD problem, to one of his PhD students, Jacob Bekenstein, saying that what happens if a hot cup of tea is thrown into a black hole. Hot cup of tea is a thermodynamic system. It has entropy, it has temperature. But on the other hand, if you see black hole is just a space-time solution. So the question is to compare a black hole with no information of its formation, as I discussed with no-hair theorem, and to a thermodynamic object which has many degree of freedom. So is the comparison right? That was the question which was asked at that point. However, we know that second law of thermodynamics is the most sacred law which has never been violated till now. And this, many people have very strong arguments defending this, the second law of thermodynamics. So we want something which is so that the black hole, this hot cup going into the black hole should also be compatible with the second law of thermodynamics. At that time, though it was known that by any process, the area of the event horizon either stays constant or increases in any process. So Bekenstein came up with an answer in 1972. Yes, that the entropy of the black hole should be proportional to the area of the horizon. And he also generalized the second law of thermodynamics to that entropy change of a black hole plus the matter outside the horizon is positive. So we have entropy in this sense. What about temperature? Generally, a system with the finite entropy has a temperature too. So classically, nothing comes out of the black hole horizon. So what does it mean to have a temperature, if at all it has a temperature or not? So to investigate, we'll move further to quantum physics. Again, quantum physics is again a very successful theory with unmatchable precision so far, and rather highly successful theory. Some of the predictions which we will be using to understand Hawking radiation and temperature is this. All the matter is described by fields. And to understand fields, imagine that this is just a guitar string. Particles are excitations of these fields, and imagine plugging strings at different modes. So those are particles. Vacuum, which in other way is supposed to have nothing but space-time, is filled with fluctuating quantum fields due to quantum uncertainty. And this fluctuating quantum fields, because of quantum uncertainty, gives pair production. So that particle pairs can be created and annihilated. So this is the basic picture of quantum fields in flat spacetime. Hawking radiation. What would happen to quantum fields in the vicinity of black hole horizon? So in most good sense, pair production happens near the horizon, and one particle which travels far away to the infinity and the other goes into the black hole. And the black hole pays the price of energy fluctuation to the vacuum. So in this sense, black hole is losing its mass and reducing. So to an observer at infinity, black hole seems to be radiating. Hence, black hole has a temperature which is called the Hawking temperature. And this is again a Gautam picture where these modes can be seen going outside. So conclude. Black holes are thermodynamic objects which have temperature and entropy. Strangely, the entropy is proportional to area than usual volume dependence in standard thermodynamic systems. However, the microscopic understanding of entropy and Hawking temperature is still unknown. So black holes are still very fascinating objects, and still a lot is there to know about these objects. That's it from myself. Thank you very much.
There's a question on black hole. I think many of you are interested. So what was the answer of this thing of T and black hole?
So the generalized second law says that the entropy of the black hole as well as the output inside will increase. So it says that the entropy of the black hole will increase on account of things of inside higher.
Temperature of this T.
Temperature of the T. Temperature of the okay, well it's inside.
We could equilibrate it with this temperature of the black hole.
Yeah, it should.
Second law says that.
Second law simply says that the entropy should increase.
Yeah, entropy, but entropy is driven by for any equilibrium system. Entropy is driven by the temperature. Okay.
Yes.
So the temperature should remain or reach a constant value at equilibrium.
Yeah. So this will be like a reversal process, of course.
Yeah.
Sure. Yeah. So definitely the area will increase in that, which is equal to the entropy increasing. So obviously, corresponding to that increase in the area, there will be some mass increase. And the temperature is mostly associated with the mass. So you can write like what happens to that, and it's inversely proportional. Temperature will go down. Just to happen.
But there was no way that temperature is intrinsic property, so it is independent of mass.
Oh well. Okay. So it depends on the mass. Okay.
Thank you.
Thank you.
Okay, so our last speaker happens to be Noor, but Noor is not present. Maybe he's busy in another talk or something. So there will be no representation of CBMS experimental, unfortunately. So we end this session here, and we should accumulate over here at 4:30. So at 4:30, we are scheduled to begin our debate competition. So we take a break of say 30 minutes, and we accumulate here maybe at 4:30. Okay. So the tea will be, I think, before the talk, before the Professor Menon start. Okay. So for the timing, only water. Yes. Okay, so good afternoon, everybody. So we are here in the second phase of the celebration of Science Day. In this session, we have a debate, and the topic of the debate is quite provocative. That it says science in the pre and post-independence era, are we going uphill and downhill? Okay. So the house is kind of arranged the thing in that way that there will be 6 speakers, and among the 6 speakers, 3 will be speaking for the motion. For the motion means in their opinion, the post-independence era was ever fruitful and it is going uphill. And there are 3 speakers who will be speaking mostly against the motion that we are not going uphill. Rather, the pre-independence era were more fruitful with respect to scientific achievements. So the rules are very simple. So you have to be finish your talk by or your argument by 5 minutes. In the 4th minute, we will ring a bell, and then you have to conclude by the 5th minute. So we will be sequentially calling, 1 for the motion and 1 against the motion. And I request you to kindly stick to the time schedule. So there are 6 speakers: Ajay Kumar Shah, Ardhendu Pal, Devashish Mitra, Shukla Chibundal, Shonali Sen, and Surya Narayan Panda. We all welcome the speakers for this session. And so I first start with Ajay Kumar Shah, who happens to be our Hindi teacher also. So he will be speaking for the motion, that is, the science is growing post-independence. Ajay, you have 5 minutes.
आज की प्रतियोगिता हेतु यहाँ उपस्थित परम आदरणीय प्रोफेसर महोदय एवं आज की प्रतियोगिता के निर्णायक मंडल, यहाँ उपस्थित उपकुल सचिव महोदया एवं समस्त अधिकारीगण एवं प्रिय साथियों, मैं सभी को प्रणाम करता हूँ। आज की वाद विवाद प्रतियोगिता का जो विषय है, स्वतंत्रता पूर्व और स्वतंत्रोत्तर भारत में विज्ञान, क्या हमारा कदम उत्कर्षता की ओर है या अपकर्षता की ओर। तो मैं सबसे पहले ये कहना चाहता हूँ कि ये जो विषय है, ये इसके विषय का मूल अर्थ है कि हमारे देश में विज्ञान का विकास और उसका मूल्यांकन कर ये निकालना कि हम आगे की ओर बढ़ रहे हैं या पतन की ओर जा रहे हैं। तो मैं कहना चाहता हूँ कि ये विषय चूंकि विज्ञान के छात्र से या विज्ञान से जुड़े लोगों से संबंधित है, मैं एक साहित्य से संबंधित व्यक्ति हूँ, तो इस पर कितना मूल्यांकन मैं कर पाऊंगा या मेरे द्वारा मूल्यांकन शायद हास्यास्पद हो, लेकिन मैं अपने विज्ञान स्तर से कुछ बातें आपके समक्ष रखना चाहता हूँ। मेरे अनुसार जो आज का विषय है कि स्वतंत्रता के बाद यानी स्वातंत्र्योत्तर में विज्ञान का जो विकास हुआ है वो किसी भी दृष्टि से हम पतन की ओर या अपकर्षता की ओर नहीं मानेंगे, हमें नहीं दिखता। क्योंकि आप स्वतंत्रता से पहले देखें तो हमारा विज्ञान कितना विकसित था, उसका दायरा या उसका क्षेत्र कितना विकसित है। अगर हमारा विज्ञान स्वतंत्रता से पहले इतना सक्षम थे तो हम किसी देश का क्यों गुलाम हो गए थे। देश की प्राधीनता का सबसे प्रमुख कारण है कि हमारा देश विज्ञान के क्षेत्र में पिछड़ा हुआ था। आप आजादी से पहले जाएं तो हम पराधीन थे, इंग्लैंड का था, उसके हमारे देश में कई देशों ने, फ्रांसीसियों ने, पुर्तगालियों ने कब्जा किया है और व्यापार किया। उससे पहले मुगल का शासन था। मुगल में हम देखते हैं मुगल काल में क्या हमारे विज्ञान के क्षेत्र में उपलब्धि है। हमें बड़े बड़े किलों या वास्तुकला के क्षेत्र से ज्यादा हमें कुछ नहीं मिलता। भारत में विज्ञान का विकास का प्रारंभ जो है एशियाटिक सोसाइटी की स्थापना और 1857 में 3 विश्वविद्यालय, कलकत्ता विश्वविद्यालय, मद्रास विश्वविद्यालय और बम्बई विश्वविद्यालय की स्थापना के उपरांत कई विश्वविद्यालय या संस्थान, अनुसंधान संस्थान भारत में स्थापित होते हैं और विज्ञान के क्षेत्र में अनुसंधान कार्य जारी होता है। हम ये बात कर करके स्वतंत्रता पूर्व के जो हमारे वैज्ञानिक हैं, मैं उनका महत्व कम नहीं करना चाहता हूं, क्योंकि उनका भी अमूल्य योगदान है। बहुत ही जो भी हमें सीमित रूप में विज्ञान के विकास हुआ है, सीमित ही है लेकिन बहुत ही बहुमूल्य है और बहुत ही महत्वपूर्ण है उनका योगदान। हमें स्वतंत्रता के बाद, या मैं अपनी बात रख रहा हूं कि स्वतंत्रोत्तर भारत में विज्ञान जो है उत्कर्ष की ओर है, इसका मूल्यांकन हम कई दृष्टियों से देखना है। हमें इसका मूल्यांकन अमेरिका या यूरोपियन देशों या रसिया ऐसा विकसित देशों के साथ नहीं करना चाहिए। हमें तीसरी दुनिया के साथ भी इसका मूल्यांकन करना चाहिए। जो द्वितीय विश्व युद्ध के बाद एशिया और अफ्रीका महादेश में भारत के आजादी के आसपास कई देश जो स्वतंत्र हुए, तो उसका भी देखना चाहिए कि वहां पे विज्ञान का कितना विकास हुआ है और उस परिप्रेक्ष्य में हमारे देश में विज्ञान का कितना विकास हुआ है। हमारा देश जब आजाद हुआ तो हमें अंग्रेजों ने किस हालत में छोड़ के गए और किन परिस्थितियों के से गुजरते हुए हमारे देश के वैज्ञानिकों ने जो भी प्रगति की है या जो भी हमने उपलब्धि हासिल की है, वो किन परिस्थितियों से गुजरते हुए हासिल किए हैं। हम सभी जानते हैं कि जब हमारा देश 1947 में आजाद हुआ तो एक गहन सांप्रदायिक तनाव के साथ और सांप्रदायिक विभाजन के साथ, देश के विभाजन के साथ आजादी मिली, जिसका परिणाम यह था कि उस समय हमारा देश शरणार्थियों की समस्या, अपने ही देश के लोग अपने ही देश में लाखों की संख्या में शरणार्थी बन के थे। वो छत बिछत घायलों में थे, कैंपों में रह रहे थे, ना उनके पास घर है ना यह है। इन सभी समस्याओं से जूझते हुए हमारे देश ने परमाणु ऊर्जा के क्षेत्र में, अंतरिक्ष के क्षेत्र में, चिकित्सा के क्षेत्र में, कृषि के क्षेत्र में गहन उन्नति की है। कृषि के क्षेत्र में यह था कि हम अपने देश में अपने खाद्यान्न के अनाज के तक भी हम उत्पादन नहीं कर पाते थे, किंतु आज हम स्वतंत्र हैं क्षमा कीजिएगा, हम अपने अनाज की जरूरत के अनुसार उत्पादन भी कर रहे हैं, निर्यात भी कर रहे हैं। हमारा इसरो आज एक ही बार में मंगलयान में अपना मंगल ग्रह पे अपना मंगलयान स्थापित किया। आप देखेंगे कि परमाणु ऊर्जा के क्षेत्र में हम देखें तो 74 में हम लोग असफल ना हुए, किंतु 1998 में हमने सफलता हासिल की। यूरोपियन और अमेरिकन कंट्रीज ने हमारे देश में जो विज्ञान का विकास हो रहा है उसमें गहन निगरानी रख रहे हैं अंतरिक्ष के माध्यम से। आप जानते हैं कि 1974 में जब हम परमाणु परीक्षण किए तो अमेरिका ने कई CVT समय समाप्ति के कारण मैं नहीं बोल पा रहा हूँ।
Any concluding remark?
Yes. Yes. ओके, धन्यवाद सर। हम ये कहना चाहिए, निष्कर्षतः कर सकते हैं कि आज विज्ञान के बदौलत हम खाद्यान्न में निर्भर हैं, अंतरिक्ष चिकित्सा के क्षेत्र में बहुत उन्नति किए हैं। आपका हार्ट या ऑर्गन ट्रांसप्लांटेशन के क्षेत्र में हम सस्ते में, पूरी दुनिया सस्ते में हम सफलतापूर्वक कार्य कर पा रहे हैं। आपका अंतरिक्ष में 104 सैटेलाइट हम एक साथ, दुनिया पहला देश ऐसा बना है कि प्रक्षेपण किए हैं। तो इस कारण से हमें कहीं नहीं लगता किसी भी क्षेत्र दृष्टि से कि हम पिछड़ रहे हैं विज्ञान में। आज IIT भारत जो 1962 में स्थापित हुआ था, वो आज देखिए दुबई में पहला कैंपस खोलने जा रहे हैं। हमारा विज्ञान सिर्फ भारत तक सीमित न रह करके विदेशों में भी हम प्रसारित कर रहे हैं। धन्यवाद।
So, according to Ajay, so India is actually progressing towards the scientific acumen, and after independence, India. So there are two countries that were get independence from British. So you said that the British government, they were not allowing India to do research. So we must be thankful to our previous prime ministers who actually make this 5 years plan, and up to, I mean, based on whose, what should I say, the alumni, we have made all this DRDO and ISRO, whatever you have said. So India is progressing very much after the independence. Thank you, Ajay. And next week, against the motion, I will call Mr. Devashish Mitra, who will be speaking that pre-independence era was better than post-independence.
নমস্কার, সবাইকে বিজ্ঞান দিবসের অনেক অনেক শুভেচ্ছা। আজ আমি এমন একজন মানুষের কথা দিয়ে শুরু করব, যিনি মানে প্রথাগত বিজ্ঞান শিক্ষা না নিয়েও বিজ্ঞানকে এমন এক জায়গায় নিয়ে গেছিলেন যা আমাদের ভারতের মুখকে অনেক উজ্জ্বল করেছিল। তিনি হলেন গোপাল চন্দ্র ভট্টাচার্য। তিনি হলেন কীট সমাজবিদ্যা বা ইথোলজির প্রতীকৃত। তার অনেক লেখা থেকে আমরা জানতে পারি, এবং তিনি একটা মেছো মাকড়সা নিয়ে কাজ করেছিলেন, যেটা 1936 সালে প্রকাশিত হয়েছিল। এবং আচার্য জগদীশ চন্দ্র বসুর বিজ্ঞান মন্দিরে তিনি কাজ করেছিলেন বটে, কিন্তু তাকে উচ্চতম কোনো বিজ্ঞান শিক্ষা তখন দেওয়া যায়নি। যদি দেওয়া যেত, আজকে ভারতকে কিন্তু অনেক বড় জায়গায় তিনি নিয়ে যেতে পারতেন। তো এটা ছিল তখনকার দিনের বিজ্ঞানের প্রতি ভালোবাসা, আন্তরিকতা, আনুগত্য, যেটা এখন যারা প্রথাগত শিক্ষা নেয় অনেকের কাছ থেকে অনেক কম পাওয়া যায়। আমি মনে করি স্বাধীনতার আগে বিজ্ঞান শুধু চর্চার বিষয় ছিল না, বিজ্ঞান ছিল সাধনা, বিজ্ঞান ছিল মৌলিকতায় ভরা। তাই আমরা অনেক সাধক বিজ্ঞানীকে পেয়েছি। তার মধ্যে হলেন আচার্য জগদীশ চন্দ্র বসু, প্রফেসর সত্যেন্দ্রনাথ বসু, মেঘনাথ সাহা, এবং মহিলাদের মধ্যে বিশেষ করে আমি বলতে চাই যার নাম, তিনি হচ্ছেন বিভা চৌধুরী, শম্ভুনাথ দে, শান্তিস্বরূপ উপাধ্যায়, মধুসূদন গুপ্ত। তো এছাড়াও তো অনেক বিজ্ঞানী আছেন, রামানুজন, মানে সিবি, যার জন্য আজকে আমাদের এই সায়েন্স ডে, যিনি নোবেল পুরস্কার পেয়েছিলেন, সিভি রামান, প্রত্যেকেই ছিলেন, প্রত্যেকেই আমাদের বিজ্ঞানকে সেই সময় সমৃদ্ধ করেছিলেন। এবং আমরা সেই একটা সময় থেকে যখন স্বাধীনতার পরে যখন এসে দাঁড়ালাম, তখন আমরা কি দেখলাম? তখন আমরা কিন্তু আমাদের বিজ্ঞানটাকে উন্নতি করেছি, আমাদের প্রযুক্তি দিয়ে উন্নতি করেছি, কিন্তু প্রযুক্তি দিয়ে উন্নতি করতে করতে গিয়ে আমরা পরিবেশকে দূষিত করে দিয়েছি। পরিবেশ দূষিত হয়েছে,
আমাদের বায়ু দূষিত হয়েছে, যার জন্য আমাদের বিশ্ব উষ্ণায়ন সৃষ্টি হয়েছে, যে বিশ্ব উষ্ণায়নের জন্য আজকে আমাদের যে হিমবাহ গুলো গলে যাচ্ছে এবং সমুদ্রের জলস্তর বৃদ্ধি পাচ্ছে। আজকে সব থেকে আমার চোখে দূষিত যে ব্যাপারটা লাগে বা কলুষিত করেছে বিজ্ঞানের এই প্রযুক্তিগত ব্যাপারটা, সেটা হচ্ছে প্লাস্টিকের ব্যবহার। আপনি পাহাড় থেকে নিয়ে সমুদ্র তট অব্দি যান, প্রত্যেকটা জায়গায় প্লাস্টিক ছড়ানো। এই হচ্ছে আমাদের আধুনিক বিজ্ঞানের দান। আমাদের হাতে মোবাইল এসেছে, আমরা দিকে দিকে টাওয়ার লাগিয়েছি, কিন্তু আমরা পাখিদের কলকাকলি বন্ধ করে দিয়েছি। এখন আর শালিক পাখি, চড়াই পাখির কিচিরমিচির শোনা যায় না, তাদের কলতান আমরা বন্ধ করে দিয়েছি। আমরা কিন্তু এখানটায় অনেক পিছিয়ে যাচ্ছি, তাদেরও আমাদের বাঁচতে দিতে হবে। আজকে আমাদের শিল্পের জন্য, শিল্প আমরা সৃষ্টি করেছি বটে, কিন্তু আমরা গঙ্গা দূষণ করে চলেছি ক্রমাগত। এই আমাদের আধুনিক বিজ্ঞানের, আমার মনে হয় স্বাধীনতার পরে আমরা এই জিনিসগুলোকে একবার আমাদের ভাবতে হবে। এই সমস্যাগুলো কিন্তু আমাদের সৃষ্টি হচ্ছে। আমার মনে হয় যে আমাদের আর একটা বিষয় ভাবতে হবে, যেটা হচ্ছে আমরা যখন প্রযুক্তিগত ভাবে সমস্ত আমরা সকাল থেকে নিয়ে আমাদের রাত অবধি আমরা প্রযুক্তি নির্ভর হয়ে যাচ্ছি। আমি একটা উদাহরণ দিতে চাই, যখন আমাদের এই প্যান্ডামিক সিচুয়েশনে আমাদের স্কুল কলেজগুলো বন্ধ, প্রত্যেকটা বাচ্চাকে অনলাইন ক্লাস করতে হয়েছে, সে সময় কিন্তু গ্রামের যারা আমাদের দরিদ্র ছাত্রছাত্রী, তারা কিন্তু সবসময় পারেনি অনলাইন ক্লাস করতে, কারণ সেই সুযোগ সুবিধা তাদের কাছে পৌঁছে দিতে আমাদের বিজ্ঞান, স্বাধীনতার পরবর্তী বিজ্ঞান এখনো পারেনি। সুতরাং একবার ভাবতে হবে যে আমরা কতটা পিছিয়ে আছি এখানে আমাদের উন্নতিতে। সুতরাং আমরা সেই মহান সাধক যারা আমাদেরকে মানে প্রত্যেকটা মুহূর্তে তারা নিজেরাই একটা এখন প্রতিষ্ঠান হয়ে গেছে, তো তারাই আমাদের আজকে ঠিক মতো গাইড করতে পারছেন না। তাদের মতো কেউ নেই যারা আমাদের কাছে গাইড করবে। তো আমাদের যে মানে দূষণগুলো সৃষ্টি হচ্ছে, এই দূষণগুলো কিন্তু আমরা প্রযুক্তি আর বিজ্ঞানের উন্নতির সঙ্গে সঙ্গে ছড়িয়ে দিচ্ছি। এটা নিয়ে কিন্তু একবার ভাবতে হবে। আজকে বিজ্ঞানের যারা এখানে, আমরা তো এখানে চাকরি করি, আমরা এখানকার বিজ্ঞান সাধনা হয়তো করি না, কিন্তু যারা এখানে বিজ্ঞান সাধনা করেন বা রিসার্চ করেন, তাদেরকে বলবো যে এই নতুন ভাবে একবার ভাবতে। সবাইকে অসংখ্য ধন্যবাদ, নমস্কার।
Mr. Mithu. So he stated against the move that pre-independence era was fine, and he mostly talked about pollution, which is rather global than being Indian, and also technology, uses of technology. So it's a global perspective. Anyway, so we next call Mr. Ardhendu Pal. Ardhendu will be talking. Yeah. So Ardhendu will be talking on the topic that according to Ardhendu, India is achieving something post-independence. Ardhendu,
first, I want to tell that what my fellow speaker spoke, he either on focusing on the development of science, he have focused on pollution and global warming. Good afternoon, everyone present here on the occasion of Science Day. So, science is a continuous process of learning and development for the community, and regular process of going forward and developing something for the entire community. So it is always progressing and going forward, and yes, its pace of growth may vary from time to time, which doesn't mean that it is going backward. So now I am focused in two periods, like before independence and after independence. So India was under the British rulership for around 200 years. So in the early 19th century, when British tried to introduce education in the Indian system, so many subjects like science, history, and all the other things which have been introduced by the British rulers, and Indian community that time thought the many subjects, including science, to not be the Indian culture, that is the British culture, forcefully introduced on the Indian people. So that time they don't took it positively, and rather tell that they rejected it. But as the time passed on, and people from Indian community understood that without education, without taking the knowledge of those things, they cannot fight with the British. And in the mid 19th century, going forward, many Indians showed interest in various various subjects and excelled in many subjects. In mid 19th century, in the leadership of Raja Ram Mohan Roy, a petition was submitted to establish the Western culture of education in India and establish many universities which will treat this taught this Western culture to the Indians. And from the mid 19th century to end of 19th century, many universities have been set up, and these universities have produced a lot of esteemed fellows and jewels and the leaders to our society, who have in future who became the icons and heroes and the path maker of this Indian society. In the early 20th century, the first research activity has begun in India. And in 1920, the Meghna Shah has proposed its equation. In 1924, the Bose-Einstein conversation have been published, and in 1928, C V Raman has declared his discovery of Raman Effect, and on 1930, he has awarded Nobel Prize. And this was an golden decade of Indian science before independence. And after that, various esteemed institutes like CSI, IISc, ISCS, Indian Academy of Science, and many more have been established before independence to take forward the Indian scientific activity. Now let's go to the next period, that is the post-independence era, in which India has tremendously progressed successively. So first, various research and educational institutes have been developed, like IITs, IIMs, ISAs, and many more, which are giving thousands of educated students and research scholars who are taking forward the Indian science regularly. And many organizations which are built to structure and organize the Indian scientific and educational activities, like DAE, DST, DRDO, ISRO, and many more. In 1944, the first nuclear program has been started in India, headed by Sir Homi Bhabha. And the continuous progress and culture with this nuclear program. In 1974, India first tested its nuclear weapon, nuclear bomb. And on 1975, India first launches its satellite Ashoka from Soviet Union. But now India became self-independent to prepare its own satellite as well as send it to the space by its self-made rocket. And India led the two successful space missions, that is Chandrayaan and Mongolyan. In India's defense research system has also gifted India Agni and Prithvi, the two deadly missiles, to make the defense sector much more stronger. And India, as the British left India as an underdeveloped country, when, as my fellow speaker Ajay sir has already told, that the production of wheat grains are very much, very less production of the wheat grains are being done at that time. And with regular research with our fellow researcher on this area has able to find out the good strains of wheat grains and many grains, which make in 1970 India self-independent to huge production of the grains. And the green revolution is told like green revolution. It is told as green revolution, which made India self-dependent to not only feed its own countrymen but also supply it to outside India. In India has excelled tremendously in the medical facility. In 1968, Sir Hargobind Khurana has received the medical Nobel Prize in medicine, and India has become the huge hub for the production of drugs and vaccines and export it to the developing as well as the developed countries. And various critical cases have been solved by the Indian doctors very fruitfully and successfully. And the supercomputer, which is the very important topic. A few minutes, that is which is already first developed in 1991, and the recent 9 supercomputers are being established, and SN Bose will also be the part of that. And looking into all of this, it is very much clear that India is successively progressing in the science, and in upcoming future it will more rise uphill, and the new project Make in India will also keep its fruitful impact in this growth. Thank you.
Thank you, Arjit, for strongly presenting his argument and correctly speaking about Professor Swaminathan, who was the father figure of this green revolution, and followed by many other, like there was white revolution and other very scientific institutes have been developed and other missions have been developed. Very good. So now I request Shoposhachi Mondol, Mr. Shoposhachi Mondol, who will be speaking against the move, that is, India is not progressing much in the pre-independence era.
নমস্কার। আমার মনে হচ্ছে উই আর গোয়িং ডাউন হিল, কারণ আমরা যদি একটা তথ্য বা একটা স্ট্যাটের দিকে দেখি যে বর্তমানে ভারতে 1.2 মিলিয়ন রেজিস্টার্ড ডক্টরস আছে এমসিআই এর তথ্য অনুযায়ী, কিন্তু আমাদের দেশে বর্তমানে ওভার 2 মিলিয়ন প্র্যাকটিসিং অ্যাস্ট্রোলজার্স আছে, জ্যোতিষী। তো তাহলে আমরা কি উপরের দিকে যাচ্ছি না নিচের দিকে যাচ্ছি? আমাদের হয়তো মনে হতে পারে যে স্বাধীনতার আগে তো এই সমস্ত কুসংস্কার জ্যোতিষী আমাদের দেশে অনেক বেশি ছিল, কিন্তু আমরা যদি আরেকটা তথ্য দেখি যে স্বাধীনতার সময় ব্রিটিশরা যখন আমাদের ছেড়ে যায় তখন আমাদের লিটারেসি রেট ছিল 14%, সেটা আজকে 74% এসে থেকেছে। তাও আমাদের মনে হচ্ছে যে এগুলো যখন পুরোপুরি নির্মূল হয়ে যাওয়ার কথা, কিন্তু আমাদের দেশে এগুলোর সংখ্যা ক্রমে বেড়েই চলেছে। আমরা কি একটা তথ্য জানি যে কোভিড এর সময়ে বেসরকারি হসপিটালগুলোর রেভিনিউ প্রায় দ্বিগুণ হয়ে গেছে, কিন্তু তার সাথে সাথে অনলাইন অ্যাস্ট্রোলজিক্যাল কনসালটেশনের রেভিনিউ দ্বিগুণ হয়েছে। অনলাইন কথাটা এখানে ইম্পর্টেন্ট, কারণ অনলাইন বা ডিজিটালি লিটারেট কারা? মডার্ন জেনারেশন। তো তারা আজকে জ্যোতিষের দিকে ঝুঁকছে অ্যাস্ট্রোনমি ছেড়ে, সেটা কিন্তু কখনোই আমাদের এটা দেখায় না যে আমরা আপিল যাচ্ছি। তো এটা ছেড়ে যদি আমরা একটু অন্যদিকে যাই, সবাই যেটা বললো ভারতে এত টেকনোলজিক্যাল ইমপ্রুভমেন্ট হয়েছে, মঙ্গলযান থেকে শুরু করে গ্রিন রিভলিউশন, ঠিক আছে, কিন্তু শুধুমাত্র টেকনোলজিক্যাল রিভলিউশন দিয়ে বা টেকনোলজিক্যাল অ্যাডভান্সমেন্ট দিয়ে কি আমরা বিচার করতে পারি যে কোনো দেশ কতটা সায়েন্টিফিক্যালি প্রোগ্রেসিভ? আমরা সেটা করতে পারি না। তার জন্য আমরা যদি একটা উদাহরণ দেখি যে আমেরিকা, আমরা জানি যে আমেরিকা আজকে পৃথিবীর অন্যতম বিজ্ঞানে উন্নত দেশ। তো সেই দেশের রাষ্ট্রপতি যখন বলে যে গ্লোবাল ওয়ার্মিং বলে কিছু হয় না, সায়েন্টিস্ট ডু নট নো, তাহলে সেই জায়গায় আমাদের কিন্তু ভাবতে হবে যে সত্যি যে টেকনোলজিক্যাল অ্যাডভান্সমেন্ট দিয়ে কোন দেশের বৈজ্ঞানিক উন্নতিকে ব্যাখ্যা করা যায়। সেই দেশে কোভিড এর পিক টাইমে যখন মাস্ক না পরার বিরুদ্ধে আন্দোলন হয়, তাহলে কিন্তু টেকনোলজিক্যাল অ্যাডভান্সমেন্ট কোনো গুরুত্ব রাখে না। তো সেই একই ক্ষেত্রে যদি আমরা ভারতে দেখি, তো ভারতেও একই জিনিস হচ্ছে। ভারত যদি সত্যি স্বাধীনতার পরে উন্নত হতো, তাহলে আমাদের দেশে প্রতি বছর ডাইনি সন্দেহে কয়েকশো মহিলাকে হত্যা করা হতো না। আমাদের দেশে কোভিড এর সময় যখন গোটা পৃথিবীর বিজ্ঞানীরা লড়াই করছে, হঠাৎ করে কোনো বাবাজি কোনো প্রোডাক্ট নিয়ে চলে এলো কোভিড কিওর বলে, এটা অন্তত হতো না। তো সেই জায়গায় যদি আমরা একটা জিনিস ভাবি যে আমাদের দেশে একসময় দর্শন চর্চার কেন্দ্র ছিল ফিলোসফি, কিন্তু সেটা কখন বন্ধ হলো? যখন তারা সাধারণ মানুষের থেকে দূরে সরে গেল। দর্শন যখন শুধু শোন, জাস্ট লিসেন হয়ে যায়, তখন কিন্তু দর্শন দর্শন থাকে না। তো কেউ দর্শন শিখতে গেলে তখন তাকে কি বলা হলো যে ভাই দেখো, এই মুহূর্তে তুমি যাকে তুমি মনে করছো সেই তুমি আসলে কিন্তু আসল তুমি নয়। তো সেই আসল তুমিকে খুঁজে বের করাই হলেই নকল তুমির কাজ। তো কটা তুমি আছে সেটা গুনতে গুনতেই তার দর্শনের প্রতি ইন্টারেস্ট শেষ হয়ে যায়। তো একই জিনিস কিন্তু আজকে আমাদের দেশে বিজ্ঞানের প্রতিও হচ্ছে। আমরা যদি বিজ্ঞান পড়তে চাই, তো ক্লাস 10 এর পরে প্রায় 26% ছেলেরা বা ছেলেমেয়েরা স্টুডেন্টরা সায়েন্স নেয়, বাকি 74% এর জন্য বিজ্ঞানের দরজা কিন্তু চিরজীবনের মতো বন্ধ হয়ে গেল। তারা যদি তারপরেও ইন্টারেস্ট থাকে যে সায়েন্স নেয়নি, সে সায়েন্স শিখতে কোথায় যাবে? বিজ্ঞান তো তারও জানার ইচ্ছা হতে পারে। তাহলে যে দেশে সাধারণ মানুষের জন্য বিজ্ঞান শিক্ষার কোনো কেন্দ্র নেই, সেখানে আমরা কি করে বলতে পারি যে আমরা এগিয়ে চলেছি? আমার ক্রিকেট খেলতে ভালো লাগে, কিন্তু আমি ক্রিকেটার হতে চাই না, তো সেই জন্য কি আমাকে ক্রিকেটের ট্রেনিং নিতে হবে? আমার বিজ্ঞানী হওয়ার ইচ্ছা নেই, কিন্তু আমার বিজ্ঞান ভালো লাগে, তাহলে আমার কি কোনো পড়ার জায়গা থাকবে না? তো এই দিক থেকে দেখতে গেলে কি হচ্ছে, বিজ্ঞান কিন্তু একটা বিচ্ছিন্ন সাবজেক্ট হয়ে যাচ্ছে ভারতের ক্ষেত্রে, যেটা কোনো মতেই হওয়া উচিত না। তো এর ফলে কি হচ্ছে, আমরা জানি যে আমাদের দেশ কি, আমাদের দেশে যোগ, আয়ুর্বেদ থেকে শুরু করে কালারিপাইপুর মতো মার্শাল আর্ট একটা সময় প্রিভ্যালেন্ট ছিল, যে আমাদের দেশ স্বাস্থ্যের জন্য সচেতন ছিল। কিন্তু আজকে কি হচ্ছে, আজকে আমরা এতটা অবৈজ্ঞানিক ভাবে জীবনযাত্রা করছি যে আমাদের দেশ আজকে লাইফস্টাইল ডিজিজের ক্যাপিটাল হয়ে যাচ্ছে। যে হাইপারটেনশন থেকে শুরু করে ডায়াবেটিস আমাদের দেশে সব থেকে বেশি। তাহলে সত্যি কি আমরা উপরের দিকে যাচ্ছি না নিচের দিকে যাচ্ছি, কি মনে হয়? তো স্বাধীনতার সাথে এটা কোনো তুলনা আসে না, কারণ স্বাধীনতার ক্ষেত্রে আমরা কি দেখি, স্বাধীনতার পূর্ব ক্ষেত্রকে আমরা অনেক দূর পর্যন্ত নিয়ে যেতে পারি, বৈদিক যুগ থেকে শুরু করে ইংরেজ আমল পর্যন্ত। সেই বৈদিক যুগে আমরা জানি যে বৈদিক যুগের পরে ভারতের পপুলেশনের একটা অংশকে, নারীদেরকে শিক্ষা থেকে দূরে রাখা হয়েছিল। তারপরে আরেকটা যখন বর্ণ ব্যবস্থা, যেটা হরাইজন্টাল ডিভিশন ছিল, সেখান থেকে ভার্টিক্যাল ডিভিশন হলো, তো বৈশ্য সূত্র করে আরেকটা সম্প্রদায়কে পুরো আলাদা করে দেওয়া হলো। তারপরেও তারা যে বিজ্ঞানে উন্নতি করেছে সেটা অনেক, কিন্তু আজকে আমরা জানি যে বিজ্ঞান তখন একটা মানুষের ক্ষেত্রে ছিল, কিন্তু আজকে এটা কোলাবোরেটিভ হয়। তা হলেও কিন্তু আমরা সেই দিকে এগোচ্ছি না। তো সেই জন্য কে দায়ী, আমরা এগিয়ে যাচ্ছি না পিছিয়ে যাচ্ছি, এর জন্য কে দায়ী সেটা একটা আলাদা ডিবেটের বিষয়। কিন্তু এই ক্ষেত্রে বিজ্ঞান যারা সম্প্রদায় আছে বা সায়েন্টিফিক কমিউনিটি, তারাও কিন্তু দায় এড়িয়ে যেতে পারে না, কারণ আমরা জানি যে বিজ্ঞান হচ্ছে অল ইনক্লুসিভ, সবাইকে নিয়ে, কিন্তু সেটা আজকে আমাদের দেশে হচ্ছে না। যখন বিজ্ঞানীরা কথা বলেন, যে যখন শঙ্করাচার্যের কথা, বুদ্ধদেবের কথা বা রবীন্দ্রনাথের কথা আসে, তখন না এরা ধর্মীয় ব্যাপার, এরা কবি, এদের দ্বারা কিছু হবে না, এগুলো বিজ্ঞানের মধ্যে পড়ে না। কিন্তু বিজ্ঞান আমাদের কি শেখায়? কোশ্চেন করতে। তো এরা কিন্তু দার্শনিক হোক বা কবি হোক কোশ্চেন করেছিল, এদের মধ্যে কিউরিওসিটি ছিল। আর আজকে আমাদের দেশে কিউরিওসিটি কোথায় গেছে? যে টিভি সিরিয়ালের পরের এপিসোডে কি হবে। তো তাহলে আমরা উপরের দিকে যাচ্ছি না নিচের দিকে যাচ্ছি? তো এত কিছু কথা বলার কিছুই নেই, আমরা ট্রেনে বাসে যারা যাতায়াত করি সবাই জানি যে বিজ্ঞান নিচের দিকে যাচ্ছে, কারণ সেখানে পলিটিক্স ছাড়া কোনো আলোচনা হয়ই না। তো পলিটিক্যাল সায়েন্সে তাদের মধ্যে কজন পিএইচডি করেছে? কেউ করেনি। তো আমরা সবাই লাদাখের ম্যাগনেটিক হিলের কথা জানি, যেখানে গাড়ি নিচের দিকে গেলেও মনে হয় উপরের দিকে যায়। তো আমার মনে হয় আজকে সেম ইলিউশন এখানেও হচ্ছে, যে আমরা সবাই নিচের দিকেই যাচ্ছি কিন্তু মনে হচ্ছে উপরের দিকে যাচ্ছে। তো একটা কথাই বলতে চাই, আমরা তখনই বুঝবো আমাদের দেশে বিজ্ঞান উন্নত হয়েছে যখন দিনে অন্তত একবার বিজ্ঞানের এত কিছু জিনিসের মধ্যে আমরা কিছু নিয়ে ভাববো, আমাদের জীবনে যুক্তি আসবে, কথাবার্তায় আমরা লজিক্যাল হবো, রেশনাল হবো, তখনই ভারত সত্যি সত্যি আগে এগিয়ে যাবে।
Has mostly focused on learning scientific aptitude rather than learning the science itself. So it's a very good notion for today's day, National Science Day, that we should also bring the scientific notion and to question what, how, and why. Really. So next, I request Surya. Surya, you are here? Yeah. Surya will be talking on for the motion, that is India is going uphill post-independence.
When the time starts, please let me know.
Yeah.
Okay. Very good afternoon, everyone. My name is Surya Narayan Panda. I am a senior research fellow in this center, and I saw people talk about various things. Especially the previous talk, they didn't compare the how we are living now and how we were living in our pre-independence era. You just say this is lacking, that is lacking. But have you compared the mentality of the humans, Indians specifically, pre-independence and post-independence? I am just going to give this comparison. I am just going to say that what was in the science in the pre-independence era and what is now in this modern era. So in the pre-independence, I am not going to go to the Indus Valley civilization of the Vedic era. As we all know, that Charak Samhita, Sushrut Samhita, all these literatures show us that we are very much advanced in science. But when the Ingrays invaded us in the mid of the 19th century, then they have used us as per their advantages. There is science, but they used our science for their advantage. So there is scientists, like you can say that Chandrasekhar Venkat Raman was there, the Satyendranath Bose was there, Jagdish Chandra Bose was there, lots of people was there. But what is the motto of their science? They usually give popular science lectures. They just convert the science books to their vernacular languages, and some scientific experiments they do for the public purpose, so the public can understand this. That's why they created a revolution. Mainly the revolution focused that we need to change the social beliefs and the religious practices, so that people will not burn up their bride if the husband dies. So, but when we got our independence, the science is in our hand. We will use our science for the development of our people. So after that, before the independence also, there are a lot of institutions. You can say our first college focusing on the science comes in itself in Bengal. It is the Hindu college, which is known as the Presidency University or Presidency College. And the first focusing on the research comes in this ISES, which is in the Kolkata itself. But these were not focused on proper research. There is not funding. How they could do research? But when we got our independence, there is a proper funding is there. I can show you, before the 1947, there is only 0.1% of our GDP is used in the research. But after just 3 years, there is 0.5%. We established Indian Institute of Technology, which is now in the Dubai, as my friend mentioned. And there are several developments. I am going to give you only 4 examples. Okay, the 4 examples is first revolution is the green revolution. I am just focusing on the part of the food. We do not have food to eat. Most of them does not have the basic needs. So first the green revolution, we produce much more food grains. And then is the white revolution. We don't have much food to eat baby food or cheese or butter for eating. So we produce the green revolution. Then the blue revolution, recently the blue revolution, we produce much more fishery items. Then you can say the much more focused is in our defense. we have very sensitive neighbors like China, Pakistan. We have to produce better artillery, our better tanks, better missiles. So we produce all those things. Then we have the nuclear power. This is a nuclear. We have to produce the nuclear systems. So we produced the nuclear systems by this smiling Buddha in 1974, and gradually it became successful. And then you can say the much more advanced thing, like India is the hub of vaccine. India is the pharmacy of the world. So this is the thing we have developed till now. And then I will show you, we have the hub of information technology. We have the hub of space science. We have gone to the space. In 2008, 2014, we have sent the space system to the moon and also the Mars. Also, we have planned to send it to several other planets and all this. So we have going the upward. Before there were scientists who were very visionary, but gradually due to their effort, we are going much more upward. And nowadays we have artificial intelligence, machine learning. You can say we have drug delivery system. We have different applications developed by Indians. Several CEOs of the companies are Indians, man. So although this vision is seen by the at the time of the independence, mostly by the politician. I am going to at last give you one quote from the Jawaharlal Nehru. At the time of the independence, in his book, The Discovery of India, in the 1946, he has explained this. What he has said, that it is a scientific approach, the adventurous and yet the critical temper of science, search for the truth and the new knowledge, refusal to accept anything without testing and trial, and the capacity to change the previous conclusions to the face in the face of the new evidence. All this is necessary not only for the science but also for the life itself. So we want to build a society based on the science, and now we are partially successful. In the future, we will be definitely successful. This is we are definitely going up. That's my view.
So Shurjo has defended his thing that India is going uphill, especially in the funding. You said is very correct that for experimental point of view, we need to have funding. But one thing that you say that India is hub of vaccine and things, but India is not patenting. So it is someone else's patent we are making. So we should be more on technologically advanced to patent things. Okay, thank you, Shurjo. So our last speaker is Sonali Sen. So she will be speaking against the motion that India is not going uphill. It was better in the TV debate.
উপস্থিত বিচারক মণ্ডলীকে এবং আমার সকল বন্ধু যারা এখানে উপস্থিত আছেন এবং ডিআর একাডেমি, ডিআর অ্যাডমিনিস্ট্রেশন সবাইকে প্রণাম জানিয়ে আমি আজকে আমার বক্তব্য শুরু করছি। আমরা সকলেই জানি যে বিজ্ঞান ছোটবেলায় আমরা পড়েছিলাম, বিজ্ঞানের অর্থ হচ্ছে বিশেষ জ্ঞান। কিন্তু আজকের দিনে যখন আমি দাঁড়িয়ে দেখি এবং আমি নিজেও সেটা প্রচন্ড রকমভাবে ফিল করি যে আমরা প্রচন্ড যন্ত্রকেন্দ্রিক হয়ে যাচ্ছি, কোনো কিছুই যন্ত্র ছাড়া ভাবতে পারছি না। মনে পড়ে যাচ্ছে গীতার একটি শ্লোক, यदा यदा हि धर्मस्य ग्लानि भवति भारत अद्भुतान अधर्मस्य तदात्मनः सृजन्यहं परित्राणाय साधूनां विनाशाय च दुष्कृतं धर्म संस्थापनाय সম্ভবামি যুগে যুগে। আজকের আমাদের যে জীবনযাত্রা অনেকটা গীতা শ্লোকের সাথে কিন্তু মিলে যাচ্ছে। আজকে আমার আগের বন্ধু এসে বললেন যে গ্রিন রেভলিউশন, ব্লু রেভলিউশন অনেক কিছু হয়েছে, কিন্তু আজও কিন্তু দুদিন আগেও আমি দেখেছি বাজারে আলু 50 টাকা, টমেটো 40 টাকা। এবার বলো, যদি আমার এই বিপ্লবের ফলে আমাদের যে বেসিক নেসেসিটি আমরা বলে থাকি খাদ্য, বস্ত্র এবং বাসস্থান, সেটা যদি ভারতীয় হিসাবে আমরা যদি না পেয়ে থাকি, তাহলে আমার এই সমস্ত বিপ্লবের কি দরকার আছে? আমি বড় বড় যন্ত্রের কথা বলবো না, আমি একজন সাধারণ ভারতীয় হিসাবে বলতে চাইবো বিজ্ঞান আমাদের কাছ থেকে কি কি নিয়েছে এবং কি কি আমরা পাচ্ছি। আজ সবাই বলবেন যে হ্যাঁ, এখন করোনা কালে অনলাইনের মাধ্যমে বাচ্চারা পড়তে পারছে, তাদের পড়াশোনা নষ্ট হচ্ছে না। সত্যি কি তাই? স্কুল লাইফে আমরা সবাই ফিরে যেতে চেয়েছি এবং যখন স্কুল খুলছে আমরা কিন্তু সকলেই খুব আনন্দিত। এবং এই মোবাইলের কথা বলতে চাইবো, মোবাইল আজকের দিনে এমন একটি গুরুত্বপূর্ণ যন্ত্র আমাদের কাছে হয়ে গেছে যে মোবাইল ছাড়া আমরা এক মুহূর্ত ভাবতে পারছি না। কিন্তু আমাদের এই মুহূর্তে দাঁড়িয়ে যদি আমরা দেখি ডিপ্রেশন বা একাকিত্ব, এটা হয়তো সবার সাথেই ঘটছে। এবং আরেকটা রোগের কথা আমি বলতে চাইবো, যেটা এখন ভারতের মধ্যে প্রচন্ড রকম ভাবে হচ্ছে। একটি হচ্ছে স্মৃতিভ্রম বা ডিমেনশিয়া, আরেকটি হচ্ছে ডায়াবেটিস, যেটা অল্প বিস্তর সবাই আমরা ভুগছি। আমার 5 বছরের ছোট মেয়ে, সে যখন মোবাইলে ক্লাস করছে ততক্ষণ তো কিন্তু ঠিক আছে, তখন আমার মনে হচ্ছে বিজ্ঞান আমার অনেক ভালো করছে, আমি বিজ্ঞানকে খুব সাপোর্ট করছি। কিন্তু সেই যখন ক্লাসের পর আরো 2 ঘন্টা মোবাইল নিয়ে থাকে, তখন কিন্তু মাথাটা আমার গরম হয়ে যায় এবং সে বকাও খায় তার জন্য। কিন্তু এই ক্ষেত্রে আমাদের হয়তো কিছু করার নেই, বিজ্ঞানের কাছে এবার এই হেল্পটা আমাকে নিতে হচ্ছে। কিন্তু আজকের দিনে যখন আমরা খেলার মাঠকে আমরা মিস করছি, আমরা সবুজ গাছপালাকে মিস করছি, আমাদের আজকের দিনে মোবাইলের জন্য যে 2G 4G যে জিনিসগুলোর জন্য নেটওয়ার্ক আরো ফাস্ট হবে আমরা ইউজ করছি, বড় বড় বিল্ডিং আমরা বড় বড় গাছ আমরা কেটে ফেলছি, বিল্ডিং তৈরি করছি, তার ভুক্তভোগী কিন্তু আমাদের আগামী প্রজন্ম অবশ্যই হবে। কবি সুকান্ত বলে গেছিলেন, এই পৃথিবীকে আমরা আগামী দিনে শিশুর জন্য উপযোগী করে তুলবো, হয়তো আমরা সেটা দিতে পারছি না। আজকের দিনে যদি দাঁড়িয়ে দেখা যায়, ভারতবর্ষের যে যুব সম্প্রদায়, যাদের উপর পুরো দেশের ভবিষ্যৎ, সেটা কিন্তু অনেকটাই নষ্ট হয়ে যাচ্ছে এবং তার অধিকাংশই আমরা বলতে পারি হয়তো বিজ্ঞান কিন্তু অনেকটা এক্ষেত্রে দায়ী। আমি আবার বলবো, বিজ্ঞান মানে আমার কাছে কিন্তু বড় বড় যন্ত্রপাতি নয়, এবং যে শুধুমাত্র চাঁদ তারা আকাশ, এর বাইরেও কিন্তু বিজ্ঞান অনেকটা জুড়ে। আমাদের সমাজের সাথে বিজ্ঞানের প্রভাব কিন্তু অনেকটা ক্ষেত্রেই আমরা বলতে পারি। এবার আসে চিকিৎসা বিজ্ঞানের কথায়। আমাদের এখনো অব্দি কপাল ভালো যে চুল আর নখটা কাটতে আমাদের এখনো অব্দি হাসপাতালে যেতে হয় না। 2 দিন পর এমন আসবে যে এটা করতে যদি হাসপাতালে যেতে হয় আমাদের হয়তো সিটি স্ক্যান করতে হবে। করোনার সময় আমার আগের বন্ধু বলে গেলেন একদমই ঠিক কথা, যে আমরা কোনো ফেসিলিটি পাচ্ছি না। প্রবল ভাবে দেখেছি আমাদের অক্সিজেনের কমতি হয়েছে এবং আমার আশেপাশে অনেকজনকে দেখেছি অক্সিজেনের অভাবে তারা মারাও গেছে। হয়তো সবাই বলবে যেটা হয়তো সমাজের কিছু মানুষ আছে যারা এটাকে নিয়ে ব্যবসা করেছে, তারা তো সমাজেরই অংশ। তাহলে বিজ্ঞান তাহলে সেই জিনিসটা, সেই সাপোর্টটা আমাদের দিতে পারলো না। আমি যদি নিতে না পারি অ্যাজ এ কমন পাবলিক অফ মাই নেশন, যদি আমি আমার বিজ্ঞানের সুবিধা নিতে না পারি, তাহলে আমি বলবো বিজ্ঞান আমার ক্ষেত্রে ভালো? অবশ্যই বলবো না। কিন্তু সত্যি যদি দেখতে চাই, হয়তো বিজ্ঞানের আবার সবকিছু খারাপও নয়, সেটাও আমি বলবো। মানে আমি বিজ্ঞানের এগেইনস্টে বলছি মানে হয়তো বিজ্ঞানের সমস্ত কিছু খারাপ নয়, কিন্তু সেই খারাপগুলোকে ভালো করার দায়িত্ব কিন্তু আমাদের, যেটা সামাজিক বিজ্ঞানের মধ্যে পড়ে, যেটাও কিন্তু বিজ্ঞানের একটি অংশ। তাই বিজ্ঞানকে যদি ভালোভাবে আমরা ইউজ করতে না পারি, সেটা কিন্তু আমাদেরই লস। তাই বিজ্ঞানকে ভালোভাবে জানতে হবে এবং তার প্রয়োগ সঠিকভাবে করতে হবে। অতি প্রয়োগে কিন্তু সমস্ত কিছুই নষ্ট হয়ে যায়। তাই যদি সফলভাবে আমরা বিজ্ঞানকে আমাদের দৈনন্দিন জীবনযাত্রার সঙ্গে যুক্ত করতে পারি, হতে পারে আগামী দিনের জন্য আমরা একটা সুন্দর ভারত তৈরি করতে পারবো। ছোটবেলায় দেখেছিলাম বা শুনেছিলাম যে ইন্ডিয়া ডেভেলপিং কান্ট্রি, আজ এই বয়সেও সে শুনি ইন্ডিয়া ডেভেলপিং কান্ট্রি। তো আশা করি আগামী দিনে দেখতে পারবো যে ইন্ডিয়া ডেভেলপ কান্ট্রির পাশে নাম লিখিয়েছে এবং আমি আমার ভবিষ্যৎকে দেখিয়ে দিতে পারবো যে দেখো আমরা এই দেশে বাস করতাম যেখানে বিজ্ঞান এতটা উন্নতি করেছে, এবং এরকম ভাবে আমি চাইবো যে আমার দেশের নাম যেন সমস্ত বিশ্বে ছড়িয়ে পড়ে। ধন্যবাদ সবাইকে।
Thank you, Sonal. See, it has mostly been described on the social and economic problem rather than real scientific justification. So that concludes 6 talks or 6 arguments. We have 3 for the motion, Ajoy, Ordhendu, and Shurya. So they sum up that how after independence, many scientific acumen has grown, like the formation of IITs, ISARs, different research institutes, funding, and the revolutions like Green Revolution, White Revolution, Blue Revolution, etc. And there are 3 speakers, Mr. Debashish Mitra, Shobhashachi Mondol, and Sonali Sen, who mostly talked about that scientific the aptitude of Indians. That has not grown, and in that sense, India the scientific progress has been hampered a lot. So. The results of the debate competition. We have 6 talks, and everyone has presented very lucidly and very elegantly their claims. But unfortunately, we have only 2 prizes. So I request our director, Mr. Shada Sutta, to come and hand over the prizes to the winners. So we have one for the one winner for the motion and other one against the motion. So for the motion, the winner is Surjunaran Panda.
Thank you.
Congratulations. And
Really, what did I say?
If I believe now.
okay, and against the motion, we have Mr. Shotusha Chikondol.
Congratulations. Discussion with you.
Okay, so thank you, Professor Shadasmita. So we conclude the second session of this whole day program, and next we have a scientific lecture given by Professor Menon, and it will be, as Professor Menon has interacted with us. So what he actually wants is a kind of interaction. So he will be speaking for 40-45 minutes, and then he needs, he requests for interaction from students. So students are free to ask questions. So it is more on the science beyond the COVID-19 pandemic, and I think you should have several questions. Changes that India and worldwide we have faced. So it will be nice that you actually do interact with the speaker. So the talk will start at 5:45. So so first we have to call Professor Menon. Is there? Oh, okay. So
When Menon is here, I think we can actually start with introducing him.
Yeah, sure.
By the time we get started,
okay, so since Professor Menon is here, I request Professor Shadasmita to kindly introduce the speaker for today's talk.
welcome back to this last session, today's celebration on National Science Day. And I'm very happy. Isn't
From Gautam's mic.
Gautam, may I request you to kindly switch off your mic? Yeah. So I'm very happy to welcome and introduce today's speaker, Professor Gautam Menon. We have been very good friends for a long time, and it is a real privilege for me to introduce him. He is a biophysicist who was trained in statistical mechanics. In fact, his PhD thesis was very different. It was on vortices and dynamics of vortices in type 2 superconductors. So you can see how people, they change their trajectories. Science is not bound to anything. That should be a great lesson for all the young people who are present online and offline. And one of his current research interests is modeling and understanding the infectious disease, which became very, very relevant during the corona time. And he contributed quite extensively on modeling and understanding the spread of the coronavirus. And those of you who watch television regularly, he became a popular face in television. And I sometimes, call him as a TV personality in our scientist fraternity. And, and he has provided very, very important input to the policy of the government during this COVID time. So this is a very important role which a scientist has to take. He is a fellow of the National Academy of India, And I was very happy to see he has been recognized as a distinguished referee both from FPS and from IOP. So Gautam takes his refereeing, which is actually a very, very integrated part of our scientific whatever responsibility we have very seriously. He is a highly regarded scientist, and as I said, and his talk today goes very well with the theme this I was telling you in the morning, which is an integrated approach of science and technology in sustainable future. And there is an extremely important role of this interdisciplinary research. And COVID has basically taught us in modeling of this COVID. There are people in various sectors, they have come together, they have joined hands. Computer science people, the biophysicist people, the biochemistry people. There are so many different people who have joined hand in fighting this deadly virus and the pandemic that prevailed. So I hope this talk will inspire you to take a kind of attitude that science is not bounded by the boundaries, not the geometric boundaries, not the subject boundaries, nothing. Science is universal. Your goal is to understand something based on whatever training you had during many of you are PhD students. So it should be really, really important whatever training you are getting during your PhD time, you have to apply it, judicially. Whatever, problem you think, that problem can be very different from your PhD. So I think not only Gautam's speech, but his career path should be very inspiring for him. So with these few words, I welcome Gautam once again and looking forward to your speech.
Thank you so much, Tanushree. Thank you for that very kind introduction. Let me sort of just try presenting my slides and you can tell me if it works. Can you see my slides?
Yes, we see you. It's coming. It's coming.
Okay. Can you see the second slide after that?
No. You have to probably click to it.
No,
not Gautam, but click to it from now. Yes, we can see now, but it's not full screen.
Okay. Sometimes there is. Now is it full screen?
Yes, it is full screen.
Okay. And can you see the slide following that as well?
Yes.
Okay,
yes.
Perfect. All right. Okay. So thank you so much, Tanushree, for that very kind introduction. And it's a pleasure. It's a great pleasure to be back at the S.N. Bose National Center for Basic Sciences. My association with your center goes back really to around the mid-90s. I think I first came there around 1995. And then I visited multiple times in the years after that. I had close collaborators, Professor Shurji Shengupta, who was there for many years. In fact, I have many papers with him that date to his period from during the period that he was there. So I have a very close and friendly and happy association with your center. There's many wonderful evenings I've spent there, the talks I have given there. And I remember this with fondness, and I do hope to come and visit there again once we're beyond this particular stage of the pandemic. What I wanted to talk about today is a different kind of talk. Usually people use National Science Day as a way of talking about very specific things about science or nanotechnology or something like that. What I want to do instead is to think a little bit about the broad shape and structure of Indian science and how should we think about it. And there was a very specific motivation for doing this. And I'll tell you about what that motivation was. The motivation was that I was asked recently to speak about Indian science as part of a series called Reimagining India. That was the title of the series. It had a bunch of different speakers. And the idea was to explore how India might work towards a more equal and more just society. So this is not something that naturally scientists need be concerned with. Most of us are tied up very much with doing our own research. We don't worry about issues of social equity and justice. But as citizens of this country, it's important that we think about these issues because each of us has the ability or it's required of each of us that we try and understand the society we live in, its faults, its limitations, and work towards something that is good for all Indian citizens. So that's the link. There were a bunch of people here, T.M. Krishna, Anjali Bharadwaj, Romila Thapar, Nandini Sundar. All of these came from many different walks of life, many different types of training. And they came from social sciences, politics, art, and literature, etc. But the organizers of this felt that a view from the sciences might be useful, might be a sort of contrast to this overwhelmingly humanities, politics, law, etc., view of how to reimagine India. I agreed at that point, but one reason I agreed was because I realized that I would have answered exactly that question. How do I reimagine Indian science very differently if it had been asked to me 18 months before that? So, of course, what happened in that 18 months before that? And all of you know what happened. That we've been living through a pandemic for the past approximately a little more than 2 years. The first case in India was recorded on the 31st of January, 2020. We are now in 2022, February. And you can see the map of the world where you can see colors representing the numbers of cases. And you can see right now 200 odd countries in the world have reported cases of COVID-19. It has been stronger. There have been larger numbers of cases in some areas versus another. In some cases, such as Africa, we do believe we are strongly undercounting the numbers of cases that may have come from there. So that's something to remember, that even our understanding of something as important as COVID-19, what it's done to us, to the world, is really fragmentary and depends upon piecing together many disconnected pieces of information and extrapolating from that information. The picture to the bottom left is the cases in India. We saw a first peak around the 15th of September 2020, a second peak around February, March, April of 2021, and then the third peak, the Omicron peak, fairly recently. We're really down on the downswing of that particular peak. The picture, the sort of blotchy picture that you see to the right, is a very famous picture. That's a picture taken from the air, possibly from a drone, of crematoria, of bodies being burnt. And again, this is an example of where politics and science collide in a sense in terms of the counting of the number of deaths. How many people died of COVID-19 is something we don't have quite a good angle over. But it's certainly true that there's a very large gap between official numbers of people who died and the actual numbers of people who died. And as a society, as a country, we need to come to terms with that number and to understand that number a little better. So in a sense, reasoning from that picture, you can see that COVID-19 has uncovered very deep vulnerabilities in our society. On the other hand, we know that we are vulnerable. We have been exposed. Our vulnerabilities have been exposed. But on the other hand, science has risen to that particular challenge. And innovation that came out of science in its response to COVID-19 have happened at a rate that is simply unprecedented in history. Nowhere in history have we been able to develop so many scientific approaches from many, many different angles, from clinical angles, from purely scientific angles, in terms of our understanding of the science, from epidemiology, applied mathematics, computer science, etc., to think about the problem of COVID-19 and understand more about this virus, the SARS-CoV-2 virus that causes it. Just to give you one example, the usual timeline to develop a vaccine has been, before COVID-19, something like 20 years. And that's been a sort of average. And that's because it reflects a very long and tortuous procedure by which first you test a large number of candidates, you look for the efficacy, you look for the safety, you try it out on smaller groups in phase 1, phase 2, phase 3, and finally phase 4 trials. And you put all of this together. That takes time. But remarkably for COVID-19, that 20-year horizon has been reduced to a single year. We've made new vaccine platforms that we've never used really, such as the platforms of mRNA vaccines, which were first deployed for COVID-19, but now that we use them and we know that they work, we can now apply them to different types of other vaccine-preventable diseases. So now our scope has expanded. The way we understand disease, the way we can treat disease, the way we can vaccinate against disease has considerably expanded, but only because of this incredible effort that we have put in towards understanding COVID-19. So some of the advances that we've made derive from what we knew earlier, and are just, in a sense, building upon these. We've repurposed them for our current needs for understanding COVID-19. But others, like the new vaccine platform that I pointed out, and there are many, many others, many, many therapeutic interventions, many, many clinical interventions, they've relied on the creation of new knowledge, and they follow an unprecedented mobilization of science and technology on a global scale. Countries across the world, companies across the world have put huge amounts of money into kickstarting an effort directed at the treatment of COVID-19, precisely because it is a global problem. It affects all of us. It is a pandemic that leaves no country unscathed. So as we emerge from the pandemic, we can think of two possible types of trajectories that Indian science could take in the future. One option, of course, is just to imagine Indian science as it used to be 2 years ago or 2.5 years ago and simply scale it up. Okay? So it's whatever we assess it now, but just bigger than that. That calls for no particular imagination on your part or my part or anybody's part. What the pandemic has done, and the ideas that I was trying to think about at the time that I gave that talk on reimagining Indian science, was that we could now reassess where we were and decide if we wanted to change the direction of Indian science in any way. What was important? What is it that the pandemic had taught us about the importance of certain parts of Indian science, viewed very broadly? I'm not talking about very specific things like, synthetic chemistry of a particular type, or nanotechnology of surfaces, etc., tribology or anything like that. I want to think about science as a very broad field that all of us are engaged in, and try to ask what is it there in that field viewed very broadly that we might want to change, or we might want to rethink, or we might want to reevaluate in terms of now what we have gone through over the last 20 years, over the last 2 years. And it's these ideas that I want to discuss with you, and I hope you will have questions at the end of my talk, because then we can go over them in more detail and find out if there is any level of agreement. And I will say things that are provocative. I will say things that may surprise you. But I hope that together we will be able to discuss these ideas and you will go back and think about them. And then we will see how to make and create and construct a vision of Indian science that need not be the same as the one that we're used to, but is in a way more suited to our purposes. So that's like imagining a different future for us. So let me start with reminding you of something, which is the Indian Constitution. And the Indian Constitution is unique across the world in that it contains a specific relevance to science. It contains a reference to the term scientific temper. And it's Article 51AH, which among a number of different articles that list the fundamental duties of Indian citizens, it says, it shall be the duty of every citizen of India to develop the scientific temper, humanism, and the spirit of inquiry and reform. The phrase scientific temper is actually not, it's fairly old, but the use of this phrase in this particular context is due to Pandit Nehru, who wrote in The Discovery of India. And I want to read this whole quote out because it's an important quote, and I'm going to zero in on one particular part of this quote. What is needed is a scientific approach, the adventurous and yet critical temper of science, the search for truth and new knowledge, the refusal to accept anything without testing and trial, the capacity to change previous conclusions in the face of new evidence, the reliance on observed fact and not on preconceived theory, the hard discipline of the mind. All this is necessary, not merely for the application of science, but for life itself and the solution of its many problems. This is a remarkable quotation because it identifies many, many different aspects of what we would consider to be good science. Written, of course, something like 60 years ago, or more like 70 years ago at this particular point. So of these goals, of all of that Panditji lists, I will concentrate on just one. And I think that, in a sense, is fundamental to thinking about science. It is fundamental to the scientific enterprise as such. And that is very simply understanding the importance of evidence. One example is the phrase evidence-based medicine. And that's an approach to clinical practice where patients are treated based on the accumulated evidence of what has worked earlier, of the efficacy of specific interventions. So this doesn't necessarily try to establish a detailed pharmaceutical reason why medicine works or not. That's not required, although that is important in a larger way of thinking about it. It just asks, does it work? Can we prove it to work? And what is the evidence that anything that you do actually works? So to come to an independent conclusion based on the available evidence, on the synthesis of the available evidence, is a practice where both the sciences and the social sciences share common ground. And that's going to be important to us in thinking about why is it this idea of the importance of evidence and understanding evidence and the role of evidence is so fundamental to the role of science as well as to the role of the humanities in our social life. So what I want to do is to take you through a bunch of different points, and I will refer to this question of evidence. I will refer to this larger question of scientific temper when I do this. But here are some points and questions that I believe are really central to reimagining Indian science if we wanted to. If we took the second option as opposed to the first option. I'm going to illustrate all of these using the impact of COVID-19 as my example, so that it's possible to relate to these ideas a little better. So my first point is that understanding the role of science is essential to being a good citizen. And even here, the question of what do you mean by a good citizen is an interesting question. Is it someone who just obeys laws, obeys rules? That would be one way of defining a global citizen. Listens to the government of the day, that's another way of defining what a good citizen is. But I mean something different. And of course, this question of what is a good citizen itself could fill up an entire seminar or a couple of seminars, if not more, and a large amount of discussion. But I mean something very specific. I simply mean someone who is broadly committed to the ideas outlined in the Indian Constitution, including our democracy. A commitment to democracy as well as to the Indian Constitution is what I will call a good Indian citizen. That includes the requirement to question things that government does. That includes the requirement to assess critically actions of your own elected government, to be objective, but always with reference to this founding document of the Indian nation, the Indian Constitution. In order to participate fully in democracy, when you vote, when I vote, it requires that we must exercise judgment, make choices about fairly complex issues. These judgments will require us to evaluate evidence. And so there it is that science must enter, since understanding the nature of evidence that is presented to you and to make an independent choice of what that evidence means is central to the practice of science. So here's my question. What I will do is I will explain the thing and I will end with a particular question. And that question here is, how do we ensure that we communicate the importance of science to society? Not just in terms of the fruits of science, like the one that I described earlier, but for what incorporating scientific temper into our lives and actions does for our society. How is it that we can ensure that the ideas behind science, the importance of evidence, the importance of independent thinking, how do we include them into our society? My second point is that breaking down barriers between the sciences is going to be crucial to the next generation of scientific breakthroughs. So that's what, as Professor Tanushree pointed out, we've reached a stage in our scientific lives, in the evolution of science, where we understand now the importance of being able to talk across fields, for one field to be able to speak to the other. Here are some examples. The structure of the coronavirus was discovered, a sort of spiky structure, was found out by using the electron microscope, which is a tool developed by physicists using quantum mechanics. The ability to project how fast a disease spreads is something of interest to me because I work in the modeling of infectious diseases. This is a problem that intersects both applied mathematics as well as epidemiology. So both field work, people who look at, ask how many cases are happening, how many deaths are happening. So those numbers are taken and bootstrapped into ways of projecting what the disease will do going forward. The PCR reaction, that's when you do an RT-PCR test, what that test relies on is something called the PCR, or the polymerase chain reaction. And it's required for accurate tests. These are the gold standard tests for an infection by the SARS-CoV-2 virus. But they were developed in a completely different context, looking at bacteria in hot springs, and to understand how is it that they manage to cope under these are extremophiles because they manage in extreme environments. What makes them, what ensures that actually happens? So COVID-19 reminds us that the crucial breakthroughs of the future in science will very likely come from applying technique from one field to another. And many of you are young scientists. You should be trained, and we should train it as our responsibility as older and more senior scientists, to train you to understand and recognize the importance of working in an interdisciplinary way. So here's my question. How do we develop an interdisciplinary approach to science in what we teach and communicate, without diluting, without sort of having a strange mishmash in which you don't understand any one science deeply enough? So you don't want to dilute your commitment to the rigor of those separate disciplines, whether they be physics or be chemistry or mathematics, etc. Without diluting your commitment to that rigor, how do you sensitize students? How do you sensitize people to interdisciplinary areas that sit at the boundaries or the interfaces between these different sciences? My third point is an unusual point, and this is a point that, again, typically most talks will not make. And that is that breaking down the barriers between the sciences and the humanities is important for both sides, that is, both the sciences and the humanities, as much as it is important for society. So what are my examples? Climate change, environmental degradation, agricultural productivity, hunger and malnutrition, public health inadequacies. These are so-called wicked problems. They're wicked because there is no single, simple scientific solution to any of these. You need many things to come together. You need individuals, you need communities, you need local governments, you need governments of countries, you need big multinational corporations, you need non-governmental organizations. All of these to come together to discuss from many, many different points of view what can be done about these so-called wicked problems. For COVID-19, again, as an example, it's those at the bottom of the pyramid, the poorest and the most disadvantaged, who have suffered the most. And this is completely clear across all countries, all forms of data. So whatever you may do with science to tackle these large-scale problems in the context of what we know the effects of this are and how differentially they act on people of different income levels, they must be guided by our understanding of where scientific intervention can be most effective and where our effects should be targeted. And that a scientist does not know. That's where a scientist needs to talk to the humanities to understand very specifically what it is that science can do, where can it be applied, Where can it provide maximum impetus for change? And how should we think about the larger social context of what science does? So for this, the sciences must be equal collaborators with the humanities. And if students like you, who we train, are to fulfill your responsibilities as citizens in the sense that the Constitution itself envisages, this is a responsibility that neither the sciences nor the humanities can actually evade. It is our responsibility, our constitutional responsibility, as outlined by those who wrote it. So here's my question. How do you create a vibrant engagement between the sciences and the humanities that is responsible to the others' concerns? How do we learn from each other? My fourth point is a very general point. That's ecology, biodiversity, and conservation should be a central part of thinking of our future. There are many reasons for this. The SARS-CoV-2 virus that causes COVID-19 actually came to humans from bats. What are called novel emerging diseases. 3 out of every 4 novel emerging diseases comes to us from animals. They spill over from animals. It's impossible really to think of human health in these contexts, in the context of infectious diseases, without thinking about the broader ecology of disease. In a sense, there are still parts of our country that are pristine. There are parts of India that are the most diverse, biodiverse in the world. Apart from the need to conserve them, purely for the reasons of the fact that our natural diversity should be a pride for every country. You could even think of these as sources of new value. They could provide new antibiotics. Of course, you may know that one of the main threats to public health in this country is the fact that we are running out of antibiotics. The last antibiotic that we use commonly was developed about 30 years ago. And increasingly, as bugs, as bacteria become more and more resistant to the antibiotics that are in use, you'll finally wind up in a hospital one day, some of you, maybe me, with the discovery that what is affecting you, the bug that is now lodged inside your body and giving you a disease, cannot be treated by any of the antibiotics that are currently available. So the only thing to do is to rely on an immune system to somehow fight against that. The other aspect of why thinking about conservation, biodiversity, etc. is important is that it allows you to connect with your natural environment in ways that have consequences for your well-being, both psychological as well as physical well-being. In order to do this, to look at this larger picture, you must understand how communities draw from and give to the environment that surrounds them. And from there, you can move outward towards more planetary concerns, global warming, certainly the most existential problem of our times, and the consequences of global warming, sea levels, which you can see across many parts of the Sundarban, where you can see where photos that you take 10 or 20 years apart, you can see how much the water has actually risen. Rising sea levels, pollution, and the over-extraction of natural resources that cannot be replaced. All of these questions must be seen within this prism of ecology, biodiversity, and conservation, which is why it is important thinking forward of how we can incorporate this into our scientific thinking. So here's the question. What sustainable paths exist in the face of these wicked global problems, and what can you do as an individual? So my fifth point is we must reimagine our approach to health and disease, keeping in mind the need for equal access to all. So let me remind you of some statistics. India has the highest number of stunted children in the world. It contains 19 out of 20 of the world's most polluted cities. It also has the largest number of tuberculosis patients in the world, the largest number of most sort of diseased patients in the world. And the COVID-19 pandemic has helped to remind us of these somewhat uncomfortable numbers. It's a responsibility of scientists like you and like me to try to address these questions in the interest of our society at this interface between science, medicine, and public health. So this is an uneasy interface between 3 very different areas. But it's important to think about this, keeping in mind the nature of the requirement for equity. So that's my fifth question. Again, a general scientific question, but with overlaps onto public health, overlaps onto health systems, and overlaps onto economics as well. How do you construct a public health system that works for all? And what can scientists contribute to this construction? My sixth point is that appropriate small science and innovation are crucial to reaching science to the public. And here, my specific example is something called the Foldscope, developed by the IIT Kanpur and then later Stanford Professor Manu Prakash, which is an optical microscope that is assembled from very simple components. You can print it out and then and assemble it together. It costs less than $1 to buy, and must be assembled together. So the person assembling it has some sense of ownership that is very specific to the thing that they put together. So it doesn't rely on buying complicated experiments and complicated equipment with large sums of money. This is something that you or I or a student or a school student can actually put together. What the Foldscope does, I wish I had a picture, which I forgot to put a picture here. What it does is to bring an otherwise costly piece of experimental equipment to every school, to within reach of every school. And because every student can independently assemble it, take it outside, take it home, look at things under it, it opens up ways of learning independently that were simply unavailable even a decade ago. So here my question is, can you do more than this? That's just one example. It's a particularly nice example, but can you use more using such what are called frugal innovations that don't cost very much to extend the reach of science to every student in the country? My 7th point is again an unusual one. Mathematics is important to science and to society. So let me remind you that, I mean, those of you at the SNBNCBS National Center for Basic Sciences presumably have reached there after being tested multiple times in mathematics at your school level. You've done science, you're much more familiar than the average person is. But there are few subjects that the average student hates more than mathematics. And equally, there are few subjects that are more central to modern science and technology. We use it as a tool, but innovations and the understanding of mathematics is very central to science and to technology. Even subjects that have traditionally been more descriptive than quantitative, for example, much of biology, have been enriched, have been made far more deeper. For example, our knowledge of genetics really comes from mathematical treatments from the 1930s, the 1940s and onwards. Our ability to understand the nature, the underlying nature of evolution really comes from mathematical treatment of genetics. And that's why biology as well, traditionally very qualitative, very descriptive, has been immeasurably enriched through a mathematical understanding. So our role, I mean, we have no one to blame for but ourselves. Our education system and our teaching are loaded towards evaluation and an all or nothing exam system, which is a system that many of you who are young will have faced. But this often winds up alienating students from mathematics. You know, they write the exams, they do well or badly, but they recognize that the fun out of all of this is then taken away. And that effectively also creates two classes of students, those who have some level of comfort with mathematics, as I imagine all of you do, and those who don't. And for example, when I teach, I encounter both types of students. And this is often a struggle for me to deal with students who tell me that I hate mathematics, I dropped it after the 10th standard, I don't want to see it again. Nevertheless, I'm in your class where you're teaching me quantitative reasoning and arguments that are essentially quantitative and mathematical in nature. How do I bridge that particular gap? So here's my question. How can we promote an interest in mathematics across the board? Not just in students, but also in the general public, given the importance of being mathematically literate, of understanding mathematics for day-to-day events, for understanding what the stock market might be doing, for understanding accounts, for understanding taxes, and for understanding what it is that mathematicians do, what do they strive for, what is mathematical thinking, what are the aims of mathematical thinking, how can we excite people of all ages in this particular question. My eighth point here is something that your institute does, which is to bridge basic and applied science. Very broadly speaking, across much of India and much of Indian institutions, there is no real direct link between basic and applied science. And that sets us apart from many other nations in the world which have a scientific enterprise of a comparable size. We are 4th or 5th in the number of PhDs that we produce in the year, but in a year, but we don't have that sort of relationship between basic and applied science that exists, for example, in Korea or in Japan. And the roots of this are, of course, historical. They're embedded in a culture of science in India over the past many decades that really rewards abstract thought over concrete action, over actually making things. And we can argue separately about why that's so and why that actually happened. But I just want to emphasize that this divide holds us back from the sorts of collaboration between industry and academic training that could lead to many things that are unambiguously good for our country, to employment, to increased employment, to entrepreneurship, as well as to the creation of intellectual property. All of these are important for us, and we should figure out how is it that we can make this bridge between basic and applied science in order to accomplish this. So here's my question of how do we create a vibrant applied science community in the country that can apply what we know from basic science to advancing human priorities while providing problems that basic science can address. So this is a two-way thing. I think the Nobel Prize winner Pierre-Gilles de Gennes emphasize the fact that applied science can lead to very important advances on the basic side, because they're a constant source of new types of problems, of new ways of thinking about actual problems that have to be solved, that have to be solved within a day or a week or a month, etc. So the provocation that this provides to basic science is a spur to doing better and higher quality basic science, even though it may have started off initially by thinking about a problem in applied science, a very practical problem in applied science. And if you have not read it, I will encourage you to read Professor Pierre-Gilles Lejeun's writings on the nature of science, on his public writings on the nature of science, and on the interaction between the importance of thinking about the need to think about applied science, even though he himself was a theoretical physicist. Here's my 9th point, and I think this is a particularly interesting and important point, and that's that consideration of equity and the removal of all forms of discrimination must lie at the heart of how we act in future. And this doesn't sound like something that one should say on a national science day. It doesn't seem to have anything to do with science. However, it is important, because if all of the citizens of our nation cannot participate equally in science, in the scientific endeavor, then automatically we are depriving ourselves of an important way of all of this expertise, this potential expertise, this potential new ways of thinking about it, as well as disadvantaging many people who are already disadvantaged by preventing them from going on to doing more important things that could be fundamental to us. So this, at least one change over the last decade or so, is our increased awareness of the extent of discrimination in our society. And much has been written more recently about the leaky pipeline, the fact that women drop out at various stages before they reach more senior levels. And I'm very happy that the director of the SNBNCBS National Center is a woman after I think the first woman director. That's an example, I hope, of something of a larger transformation across the country, where women will increasingly occupy positions of increased seniority, where they're in a position to set right some of these mistakes of the past many years. The number of scientists from so-called reserved categories in our top institutions remains very far from adequate. And this certainly doesn't represent the diversity of this country. And again, that's a question that we have to ask. What is it that we are doing as scientists with a social responsibility? How can we intervene to set historical wrongs correctly, to ensure that at least, roughly speaking, our institutions, the diversity in our institutions, represents the diversity in our country? So how do we move? Here's my question. How do we move towards greater equity and representation in our universities and scientific institutions, removing all forms of discrimination and encouraging diversity? 10th, again, an unusual point. And that's the point of we must revisit or re-examine or recalibrate the relationship of science to religion and belief. Often we think of science and religion and faith as being completely unbridgeable, completely different ways of looking at the world. The reason we should reapproach this, or think about it at least, of how we will conceptualize this relationship, is that the vast majority of Indians, like it or not, it's not the friends with whom you go to tea with or the people you hang out with, but really India at large. Vast majority of Indians are religious. They profess some form of religion. If you do not address this divide, you will simply prevent scientists from connecting to this much larger fraction of society. You will always be separate from them. If you are to address superstitions and practices that are discriminatory, even if they happen to be sanctioned by religion, you must be able to find the right allies. Scientists should be able to do that, to be able to relate to those allies. Only then can you expect meaningful change to occur. If you want change to happen, you have to be able to talk to people. If you have to talk to people, is starting from a point of view where you talk down to them is not a good starting point. So that's where I think it needs work. It needs work of a very unusual and a very different type that we don't think about normally, but is important, I think, for India in the future. So how do we address the gap between religion and science so that science can convey its core messages, including the need for evidence-based thinking, without necessarily casting the sciences in complete opposition to what religion does? My last point here is point number 11. That's the importance of teachers to a society. Right now, India is at a crossroads where the space for independent academic thought, you may not notice it so much in where you are, but overall the space for independent academic thought is shrinking, even as the demand for education increases exponentially from year to year. In order to be academically independent as a scientist or as a teacher, what you need is the security of a job and a living wage. And that's the US tenure system largely is intended to provide this, to provide the security of a job where you can then speak independently, as well as the means of support. However, if you look at a broader level of what happens across the world, not just in India, The shift to having temporary teaching staff in universities and colleges has meant that you create a large number of teachers who survive on ill-paid contracts that must be renewed regularly, typically at the end of a year. This strikes against the idea of academic freedom and independence, since it views teachers simply as those who deliver vehicles. It doesn't matter who you appoint at the end of the year. It's just someone who comes, spews out something in class, and then goes back. And so this is a vehicle for canned learning. And therefore, this inhibits the teachers from driving them to express only those opinions that will upset no one, because everyone wants to be reappointed at the end of the year. So the larger and larger the scope, the larger and larger the numbers of those who are functioning purely independent, badly paid, temporary jobs over years and years and years. This affects our ability, the ability of our scientists, the abilities of our teachers to express independent thoughts. And that is important for anyone who thinks about the importance of learning, teaching, and science in our lives. So how do we convince the people at large that education at all levels is important, and that those who educate, teachers, deserve the same extent of respect and support that we assign to the most valued jobs in our society? Why is it that we value someone who works on Wall Street or works on Dalal Street in Bombay at a much higher level than we do a teacher? How do we ensure that teachers are compensated at levels enough that reflect their contributions to society? And how do we equally, how do we ensure that the standards that we place on these teachers are high? So I'm kind of winding up at this point. I think I took a little less than the full 45 minutes, 40 odd minutes that I wanted to speak. I wanted to say that the pandemic has forced us to relook at our lives as no single world event has before. I mean, look back at world events in our memory, and certainly within your memory or my memory, it doesn't include an event like the Second World War, which is certainly a traumatic world event. But since then, at least since then, we have really encountered nothing that has affected the world at the scale as the COVID-19 pandemic has. And that carries with it both pluses and minuses. The minus, of course, is the tremendous scale of loss during the pandemic. But the pluses are that because things have changed, in a sense, non-perturbatively, very suddenly from what they used to be 2 years ago, it's also a good time to reevaluate our priorities in terms of how we think about science and society as a whole. So the possibility that you can change things in a transformative manner, change things completely from what they used to be, that's a real possibility if we were to take it seriously. But what it needs is both commitment to doing that, as well as certain clarity of vision. And the points that those are my points, they may not be your points. But what we need to do is to be able to discuss those and find out, is it possible to change things that keep these larger questions in mind? Are these questions important to you and to me? Are they important to our society? What is the nature of the India that we want to see going forward? What is the India that I remember when I was a young faculty member, there was this exercise called India 2020, which was an attempt to try and understand what India would look like in the year 2020. 2020 was, of course, the year of the pandemic, and I think there was not one of the proposals that were made at that time ever anticipated that we would be in a situation in 2020 which was so drastically different and would have such long-term, remarkable consequences for our country. None of us thought of that at that time. But in order to do transformational change, I want to take you back to my original statement about the need for thinking about what our Constitution says and the idea of scientific temper itself. And to do this, to make transformational change, would require that you place the idea of scientific temper, which is unique to our nation as a constitutional value, at the center of our thinking. To go back and think about what was meant, what did Pandit Nehru mean, what did the creators of the people who introduced that amendment, what did the creators of our Constitution think about when they thought about India over the next 5 years as an independent country. And what did the people responsible for National Science Day? Of course, it commemorates the Raman Effect, the discovery of the Raman Effect. Why is a Science Day important in our country? This is a time when we think about the relevance of science and what science can do. And here, what I've talked about is the need to look at science from a larger and a broader perspective. I could easily have talked about something very specific about my work in condensed matter physics or statistical mechanics or biophysics or disease modeling. But I wanted to try and present to you this very much broader picture, this set of ideas that really has to have you and me thinking about what is it that we need to do? How should we think about Indian science in the future? How can we reconceptualize it? Is there a need to do that? And if we could just shatter it and remold it together, what shape would that actually take? So here are the 11 points that I spoke about. And I'm going to leave this up here for a bit so that you can have a look at them. But I think this is probably a good time to stop. I think I took approximately about 40 minutes, which is fine. And I'd be happy to take questions for the next 20 minutes or so. And if I hope you do have questions about what it is that I have said. And because it was not a technical talk, but something that relates to many things beyond a purely technical understanding, I hope this is something that will interest you. And I look forward to the question that you ask. Go ahead. Thank you.
Mr. Menon, for this thought-provoking talk, and now we can have some questions. So, maybe we can ask questions from online. If anyone has any question.
Maybe, let me just stop presenting this so that I can see this a little better. Yeah.
So, anyone from the online? Professor Dev?
Yeah. Hello. Yeah, very nice talk actually. So I have been listening this kind of points what you have raised today, 11 points. It's very fantastic, and I think that maybe nowadays we should think very carefully how to develop groups. How to accommodate all these groups in a way so that we can develop the needed technologies by our own. So I have one question to you. Can you suggest how to dissolve the barriers among, because you know that in Indian scenario, what we have used to see that a particular group, they are trying to develop themselves only.
Yeah.
But they are not sharing, they are not actually communicating to the other specialization groups so that we can develop something. And this is really, we are lagging actually in our country. We have talent, we have everything, but we are still lagging and we are all importing the small things. So this is very painful. Can you suggest how to dissolve the barriers?
That's a very good question. I wish I had a good answer to that particular question. I think that to us is really our responsibility. We should teach our students what collaboration means.
Yes.
Often in many places, you don't want your student, I mean, there are faculty members who don't want their student to talk to anybody else, don't want to talk only to me, because they're afraid of what might happen if the student found another way of thinking about this problem or became too attached to another faculty member who they admired.
Yeah.
I think we have to solve that problem for ourselves. It comes from confidence in what you do. If you are confident in what you do, you're willing to explain, to interact, to collaborate, to have interactions with other people. And that's really our failing. If you compare us to what the US does, where you can have collaborations of multiple departments, people
Yes.
working together, because each of them is confident in what they do and they realize that they cannot do everything. They must rely on somebody else with an equivalent level of confidence and ability to be able to contribute. We can slowly get there. I think it's important. I think students should do that. Students should certainly do that. But it's our responsibility.
When we are going there in US or some other country, developed country, we are doing. But when we are coming back here, we are not following all those things actually. That is the main issue.
Yeah, no, you've raised a very important point, and I think this is something that we should do. It's our responsibility, and I hope the students do a better job when they grow up and become independent faculty members on their own.
Yeah. Thank you.
Thank you.
Okay, thank you, Mr. Dev. Anyone else from the online students? So maybe I switch to the offline. So Amita has a question.
Hello, this is Raman.
I can't hear you.
Can you hear me now?
Yes.
Okay, this is Raman.
Hi.
Okay. So thank you very much for putting very nicely several questions that many of us have thought from time to time. That was all very beautifully put. So I had several questions about these things, and I don't know if I should have time for all of them. But one of the first question I thought of was regarding scientific temper. And how we have been approaching it throughout the last 75 years, let's say, since Nehru wrote about this. So instead of talking about earlier times, let's say that for the last 30 years or so, our scientific temper, our approach to scientific temper has been driven by our understanding or our use of technology. Okay? Because when people think of what science is, they think of what they can use and what they handle every day. I mean, I'm not talking about scientists so much, but even scientists, the computers, other things. So, in my view, I don't know if you will agree with it, unless we move away from that particular line of approach and think of science and technology different as being different, we are not going to regain our scientific temper. So, do you have any idea of how that?
No, you're right that when the common public thinks about science, they're really thinking about technology. They're thinking about mobile phones and TVs and radios and so on. So that's certainly true. People are not thinking about basic science at all. My view of scientific temper is actually broad. It's a way of thinking, is my opinion. And I tried to emphasize that earlier. Scientific temper is simply a way of understanding what evidence is and what qualifies as evidence and what is good evidence and how to construct an argument using evidence. Evidence-based thinking is for me the essence of the scientific temper. If you can do that, if you can teach people how to do that in whatever context, you've already accomplished something very specific. So I find that word very interesting. I had not thought about it enough in the past. But the fact that our constitution includes that phrase, and it comes from this description of Panditji of what exactly he wanted it to do, what exactly he wanted it to accomplish. And he introduces the word, so the amendment includes the word humanism. So it's already talking about the social impacts of science and the fact that scientists should be aware of the social impacts of science. It's a good question, and you're completely right that the common person thinks about technology. Maybe it's important to separate technology and science from each other just for that reason. And to think of scientific temper as really referring to the science part of it and concentrating on that. I'm not sure how to do it, how to really do it. I'm just saying that as a philosophical idea, it's important to think about this. And one way to think about it is the importance of thinking independently to a democracy and to making the decisions that an informed citizen should make. I don't know if that answered the question. I'm sorry, but
I completely agree with you. I was just, thinking about how to sort of put it in a form for the next 20 years or for the next generation when I talk to our students or our children. Okay, but anyway, I mean, you are absolutely right. I agree with that. I don't know how far we can go with that line today, but definitely something to think about. Another question I had was regarding teaching of mathematics. So, you have been teaching and you find people who are afraid of mathematics. And your suggestion was that in India this is because everything depends on the entrance test, so people have to mug up and write something. But this fear of mathematics is universal, I think. Not only in India, everywhere else. So, how do you explain that, and how do you think we should take care of this in India? Because I don't think it's about exams.
You're completely right. It's universal. It's all across the world. And I'm sort of brought to thinking about this every time I teach. I teach a course called Quantitative Reasoning and Mathematical Thinking. And that course is a required foundation course among the set of courses that students who just joined are required to take at Ashoka University. And because of that, it has students who intend to do English, intend to do economics, intend to do philosophy, intend to do physics or biology, etc. But it's a strange mix of students who've done even calculus by grade 12, as well as people who've dropped out of mathematics by class 10 and I've never seen mathematics after that. And those students often hate mathematics. They're really happy to have stopped doing it. Some of them will go to biology because, in fact, many science students move to biology because they don't like the mathematics part that would drive them towards physics, towards the physical sciences. So what I do is to try and teach very different types of examples. I try to teach how to estimate things, how to get a feel for statistics, how to get a feel for probability, and use just lots of strange and unique examples from this, just to try and also to try and relate it to things that they understand from a social sciences or a arts perspective. I mean, what are contemporary events for which you how do you understand the stock market, for example? Is it up and down in the stock market? Is it really reflecting the efficient market hypothesis? How does that translate back into a random walk? What is a random walk? What are the relationships between different ways of thinking about it? So even if you're not an economist or investing in the market, you can look at those little wiggles up and down of the stock exchange and try and understand what is the fundamental logic that governs this. Where does that come from? And again, I think it really depends upon the nature of the example that you choose that can draw people in. I worry a little bit that our standard mathematics curriculum is just so very standardly done, written by mathematicians for mathematicians, that it doesn't account for people who may not go and do serious mathematics later. But we don't want them to be scared off completely from mathematics. That, I think, is a sort of harder line to draw. I don't know how to draw it, but I'm very interested in that question.
Yeah, so this is very important, actually, to learn mathematics at a basic level.
Yes.
Without mathematics, nothing can be done, nothing can be analyzed also.
Yes.
Yeah, and I have another question or comment about the basic versus applied division suggested. So your suggestion or maybe your comment was that the blame lies mostly with the scientists. Basic science rather than applied. You did say that it is a historical thing that we have been doing, thinking rather than doing actions. But I do not quite agree. I would rather say that it's because of the job situation that people try to join basic sciences, where at least there are some government jobs in universities and colleges. If they go to applied sciences, they will simply end up being a manager in a company rather than be part of the research and development, which is not very much in India. So, being in a different place now, what is your opinion?
No, I agree with that. There is no strong applied science base in India. And ideally, you would have companies who would want to invest in research that is applied research, but has a basic component. And that would be the real interface between basic and applied science. We don't have that. We really have missed that particular boat. Whereas, big Korean companies, Japanese companies, Samsung, etc., really put a lot of money, huge amounts of money into exactly applied research, which has a flavor of pure research. You have people doing both pure and applied research in the same laboratory. That's a source of jobs. And that certainly is one way. Encouraging a base of applied science is certainly one way of creating new jobs, creating new entrepreneurs. Again, you want to have people, unless people can build things with their hands, can conceptualize what products might be in the design of those products or the manufacture of those products, you will not have jobs being created out of that entrepreneurial energy. So we missed the boat in multiple ways. Yeah. The question is, can we set things right now by thinking about them again?
No, but thank you. Thank you very much. I don't have any other question today.
Thank you.
Gautam, I hope we can have an entire 1 hour of discussion. Quite provocating. It's a very provocating talk with many counts, and yeah. So I have only few pressing issues. One is that of the interdisciplinary research, and I think what Professor Day mentioned is like the importance of a teamwork. One reason it is discouraged in India is because our award system, we basically awards individualistic performance.
Yeah.
Because traditionally we think of all our great scientists, they were individualists. So by the time the world has changed, but India has not realized that it has to be now a team work rather than a. And that I don't know how to really convey this message. I have tried to convey this message, for example, all our academic fellowship, all but Nobel Award, anything, any kind of recognition. That basically looks at, even for giving project, in the project proposal, in the CV, they look for what this person has done independent. What does this word independence really means? And does it mean if you are a part of a big collaboration, you have not done anything? So I think this is a change of a mindset. and I really don't know how to address it. But I think several people should tell basically the scientific administrators, and also the people who are in position of power, that this is a high time this point should change.
No, you're correct. I mean, it's not just a problem in India, though. I mean, even the Nobel Prizes now increasingly are given to single people, whereas they really represent the work of large collaborations. And it's hard to identify one person as being the person to whom you want to give that particular award. There's some changes. I think, for example, I work with the India Alliance, which funds certain types of biomedical research. And there they have team science grants, which are given to a team of people, and there are certain restrictions on how to constitute that team. But that's the difference. So it's no longer an individual grant, but you look at the strength of the team, their ability to collaborate, and the ability to get together. And that, I think, is one way in which we could take this. The award system, I agree, is sort of broken in multiple ways. It's broken not just in this way, but it's also broken in other ways. And unfortunately, these are important in some level for career progression, etc. That would be a different discussion altogether. But I think trying to encourage and stimulate team science approaches and making sure that you evaluate them very carefully and make sure that it's not just one person dominating and everybody just, contributing stuff, small little pieces, but it's really a genuine interaction. That, I think, is one way out of it. And that, I think, is something that we should do. For example, Tanushree.
Yeah, and also of course, nature science, all this journal does it. I mean, where the contribution,
yes,
there's a statement of contribution.
Yes.
Unfortunately, it's not there in the ATS or ACS or whatever.
Yeah.
I think that should be, kind of as a policy.
I suspect that will happen. Because as increasingly there are these reports of plagiarism or something else or fake data, it is important. Even physical scientists and chemists will find it important to specify who did what at what stage and who's responsible for what. The biologists understand this and understand this very clearly. I'm pretty sure it has spread to the other sciences as well.
Another comment I have also in this respect about the interdisciplinary science. Very often people say it's a way of diluting science because you are not expert of anything, so you just put yourself in the interdisciplinary. So since you are one of the person who has been really battling for this interdisciplinary science, so how do you really tackle this criticism?
So I tend to think of myself as being somewhat unusual. I mean, I was supported by institutions that were happy to let me do whatever I wanted to do. I was never, they were happy to evaluate me, whether I was doing vortex lines or whether I was doing biophysics or whether I was shifted to other different types of problems on diseases. I think that is, in a sense, the strength of institutions like ours. And that's slowly vanishing. The fact the ability of people to let people do what they want, to search for their own areas and niches and develop them. Because now there's very much of a pressure to specialize, to do one area, to write lots of papers in a particular area in order to receive a certain amount of prominence. In a sense, I can see where that's coming from, because unless you do that, you don't have the sort of long-term impact. But on the other hand, I think we're losing something that way, and that we're losing precisely this ability to move between different areas, to search for something that is more fruitful, more interesting, even though it may not be the area that you're actually trained in. So I don't know, I said sort of brave things about interdisciplinarity. I did mention that it should not dilute disciplinary value. And I think that's very important. I think whatever I managed to do in thinking about diseases and models for diseases really comes from the fact that I was trained in statistical mechanics. So there are deep roots of mine that are very disciplinary. But now the leap is to think of those ideas in different contexts. And that's the first step towards interdisciplinarity. The second is just collaboration. You cannot do everything on your own. And the only way, for example, to work in biophysics is to collaborate with a biologist on a problem that neither can independently solve. So it's choosing the right collaboration that I think is important, and figuring out the nature of the problem. But I think the good collaborator, ranks at the top of any of these lists.
Yeah.
Thank you so much, Gautam. And I do hope you can visit us and we can chat for hours.
Yeah, absolutely. Yeah, I look forward to it.
Thank you.
Okay. Thanks, everybody. Thank you for the invitation. Very happy to be here. I hope I will come there again.
Yeah. So if there is no more question, then we thank Professor Menon for sending us. We conclude here. Thank you very much.
Thank you. Bye-bye.
Bye.